You think you know what makes things work. Drop something and it falls, turn on a light and it shines. The world follows patterns you can count on, but there are places in our universe where everything you believe about reality simply stops working. Places where light itself gets trapped, where time slows to a crawl, where the very idea of space breaks apart. Scientists once thought they had the universe figured out, but then they discovered these cosmic monsters that laugh at our best theories. They found places where matter forgets what it is, where information might vanish forever, and where the rules we live by every day become meaningless. We'll explore these cosmic mysteries in more depth in this video and learn what happens when the universe stops playing by our rules. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. Somewhere in the vastness of space, there are places where our understanding of reality simply comes to a stop. These aren't just distant corners of the universe we haven't explored yet. They're boundaries where the very laws of physics, the ones that govern everything we know, break down completely. We call them singularities, and they represent something quite profound about the nature of existence itself. Think about density for a moment. The air around you has a certain density. Water is denser than air. Rock is denser than water. But what happens when you keep compressing matter, squeezing it tighter, until atoms themselves can no longer hold their structure? The result is something so dense that a teaspoon of it would weigh as much as a mountain, and at the very center of this compressed matter, there might be a point where density becomes infinite. This is where mathematics starts to whisper, rather than shout. Our equations, the ones that describe gravity and space and time, they work beautifully right up until they reach this point. Then they produce results that don't make sense. Numbers that stretch toward infinity. It's as if the universe is telling us politely, but firmly, that some things remain beyond our grasp. The strangest part is that these singularities aren't theoretical curiosities. They're hiding inside black holes, scattered throughout the cosmos, like cosmic punctuation marks. When a massive star exhausts its fuel, it collapses under its own weight. The collapse doesn't stop when the star becomes incredibly dense. It keeps going, past the point where atoms break apart, past the point where even the fundamental forces that hold matter together can resist the pull of gravity. What emerges from this collapse is an object so gravitationally powerful that nothing can escape it once it gets too close. Not rocks, not gas, not even light itself. The boundary around this object, the point of no return, is called the event horizon. And somewhere inside that boundary, the singularity waits. But here's what makes it even more intriguing. These aren't rare cosmic accidents. Most galaxies, including our own Milky Way, have supermassive black holes at their centers. Millions, sometimes billions of times more massive than our Sun. They're woven into the very architecture of the universe, as if singularities are part of some fundamental design we don't yet understand. Our own galaxy's central black hole sits about 26,000 light-years away. We can't see it directly, but we can watch stars racing around it at incredible speeds, their orbits tracing out the invisible presence of something unimaginably dense. These stars move so fast that they complete their orbits in just a few years, whipping around empty space, like dancers following a partner made of pure gravity. The mathematics of general relativity predicted black holes decades before we found them. Einstein's equations suggested that if enough matter collapsed into a small enough space, it would create a region where space and time became so warped that escape became impossible. Einstein himself wasn't entirely comfortable with this prediction. The idea seemed too extreme, too far removed from everyday experience. Yet the universe appears to be comfortable with extremes. It creates conditions that push the boundaries of what seems possible, temperatures of millions of degrees, pressures that would crush any material we know, magnetic fields trillions of times stronger than Earth's. And at the heart of it all, these points where density and gravitational field become infinite. What does infinite density even mean? It's a concept that doesn't translate well to human experience. We can imagine something very dense, but infinitely dense pushes beyond imagination into pure mathematics. It suggests that at the center of every black hole, there might be a point with no size at all, yet containing tremendous mass, a geometric point, occupying no space, yet warping space and time around it. This is where physics meets philosophy in the most direct way. We're confronted with something that exists, that has measurable effects on its surroundings, yet remains fundamentally unknowable. It's a reminder that reality might contain aspects that are forever beyond direct observation or complete understanding. The story of singularities doesn't end with black holes. If we trace the history of the universe backward, rewinding the expansion of space, we arrive at an even more profound singularity. Everything we see, all the galaxies and stars and planets, all the matter and energy in the observable universe, compressed into a single point. The initial singularity from which everything emerged. This primordial singularity presents us with questions that touch the deepest mysteries of existence. What came before it? The question might not even make sense, because time itself might have begun with that singularity. There might not have been a before. No time, no space, no physical laws as we understand them. It's a humbling thought, but the entire story of the universe, all 13.8 billion years of cosmic evolution, might have begun from something we cannot fully comprehend, a point where our best theories encounter their limits, where science acknowledges the boundaries of its own reach. Yet even at these boundaries we find beauty. The mathematical descriptions of singularities, while ultimately incomplete, reveal elegant patterns. The way space curves around them, the precise relationship between mass and the radius of the event horizon, the fact that information falling into a black hole might be preserved in some form we don't yet understand. These cosmic objects also serve as natural laboratories for testing our understanding of physics. Near a black hole, space and time behave in ways that are dramatically different from our everyday experience. Time runs slower, in stronger, gravitational fields. Space itself becomes curved. Effects that are barely noticeable here on Earth become pronounced and measurable. The event horizon represents a unique boundary in the universe. From our perspective, watching from a safe distance, anything falling toward a black hole would appear to slow down as it approaches the horizon, its light becoming redder and dimmer until it fades from view. But from the perspective of something falling in, the journey would seem quite different. Time would pass normally, and the crossing of the event horizon might not even be noticeable at first. This difference in perspectives reveals something fundamental about the nature of space and time. They're not absolute, unchanging backdrops against which events unfold. They're dynamic, flexible aspects of reality that respond to the presence of matter and energy. Gravity isn't a force pulling objects together. It's the curvature of space-time itself, and objects simply follow the straightest possible paths through this curved geometry. Inside the event horizon, all paths lead toward the singularity. The curvature of space-time becomes so extreme that every direction points inward. It's a region of space where the future is singular, where all possible trajectories converge on that central point of infinite density. But perhaps the most remarkable thing about singularities is how they remind us that mystery is an essential part of understanding. Science progresses by pushing the boundaries of the known, by venturing into territories where previous knowledge proves inadequate. Singularities represent the ultimate frontier, places where our current understanding acknowledges its own limits. They stand as monuments to the idea that the universe is under no obligation to make complete sense to us, yet they also represent invitations, challenges to develop new ways of thinking, new mathematical tools, new conceptual frameworks that might one day illuminate even these darkest corners of reality. For now, they remain cosmic question marks, punctuating the structure of the universe with reminders that some mysteries run deeper than others. They suggest that reality itself might be more strange, more layered, more fundamentally mysterious than we have yet imagined. And in that strangeness, there's a peculiar comfort. The universe is not a solved puzzle. It retains the capacity to surprise us, to challenge our assumptions, to reveal new depths of complexity and wonder. Singularities are perhaps the ultimate expression of this cosmic inscrutability, points where the familiar gives way to the utterly unknown. At the heart of every black hole lies something that shouldn't exist, according to everything we think we understand about reality. A singularity, where matter gets crushed into a space smaller than an atom, yet somehow maintains all of its mass. Picture trying to squeeze an entire mountain into the period at the end of this sentence. That's the kind of impossible compression we're talking about here. The strangest part isn't just that this happens, it's that the universe seems perfectly fine with it. These cosmic monsters sit quietly in space, warping everything around them like a bowling ball pressed into a stretched bedsheet. Light bends around them, time slows down near them, and anything that gets too close simply vanishes forever. Yet somehow, they follow rules, even when those rules make no sense to us. What's truly fascinating is how black holes form in the first place. When a massive star, maybe 20 or 30 times heavier than our sun, runs out of fuel, it faces a problem. For millions of years, it's been fighting a cosmic tug-of-war. Nuclear fusion, in its core, pushes outward, trying to blow the star apart, while gravity pulls everything inward. The moment the fuel runs out, gravity wins, completely and catastrophically. The collapse happens so fast that if you could somehow watch it, you'd miss most of it in the blink of an eye. The star's core, which might have been the size of Earth just moments before, shrinks to nothing, to a mathematical point with no dimensions at all. Yet that point still has mass, still has gravity, still pulls on everything around it, with the same force the original star had. This creates what physicists call an event horizon, an invisible boundary in space where the rules of cause and effect start to break down. Cross that line, and you can never send a signal back to the outside universe. From your perspective, falling toward the singularity, time would seem normal. But to anyone watching from a safe distance, you'd appear to slow down, your image getting redder and dimmer until it fades away completely. The really mind-bending part is what happens to time itself near these objects. Einstein showed us that time isn't constant. It's more like a river that can flow at different speeds depending on how much gravity is around. Near a black hole, that river slows to a crawl. An hour there might equal years or decades in the outside universe. Scientists have actually measured this effect. We have incredibly precise atomic clocks that can detect tiny changes in the flow of time. Take one of these clocks up in an airplane, where Earth's gravity is slightly weaker, and it will tick just a little bit faster than an identical clock on the ground. The difference is tiny, less than a billionth of a second, but it's real and measurable. Black holes take this time dilation to its extreme. As you approach the event horizon, time stretches like taffy. What feels like minutes to you might be centuries to the rest of the universe. It's as if these objects exist partially outside of time itself, frozen moments where the normal flow of events simply stops making sense. Then there's the question of what happens inside. Our best theories, the ones that have successfully predicted everything from GPS satellites to particle accelerators, simply give up at the singularity. They produce infinities, mathematical nonsense, that usually means we're missing something important about how reality works. Some physicists think the singularity might not actually be a point, but rather some kind of exotic structure we don't have words for yet. Others believe that quantum effects, the strange rules that govern the smallest particles, might prevent the complete collapse we call a singularity. At those incredibly tiny scales, particles can pop in and out of existence, and space itself might have a kind of granular structure that prevents infinite compression. Stephen Hawking discovered something remarkable about black holes that nobody expected. They actually emit radiation, incredibly slowly and faintly, but real nonetheless. This happens because of quantum effects right at the event horizon, where particle pairs spontaneously appear, and one falls in while the other escapes. Over unimaginably long periods of time, this process would cause even the largest black holes to evaporate completely. The timeline for this evaporation is staggering. A black hole with the mass of our Sun would take longer to evaporate, than the current age of the universe multiplied by itself thousands of times over. The supermassive black holes at the centers of galaxies, some containing billions of solar masses, would persist for periods so long that all the stars in the universe will have burned out and gone cold long before these cosmic giants even begin to shrink noticeably. This raises profound questions about the ultimate fate of information. If you throw a book into a black hole, what happens to all the information contained in those pages? Classical physics says it's gone forever, but quantum mechanics insists that information can never be truly destroyed. This creates what's known as the information paradox, one of the deepest unsolved problems in modern physics. The centers of most galaxies, including our own Milky Way, harbor supermassive black holes that contain millions or billions of times the mass of our Sun. These aren't formed from collapsed stars. They're too big for that. Instead, they likely grew from smaller seed black holes in the early universe, gradually accumulating mass over billions of years by consuming gas, dust, and entire stars that wandered too close. Our own galaxy's central black hole, located about 26,000 light-years away in the direction of the constellation Sagittarius, has a mass 4 million times greater than the Sun. We've actually watched stars orbit around this invisible monster, using their motion to map out the shape of spacetime itself. Some of these stars complete their orbits in just 16 years, reaching speeds of thousands of miles per second as they whip around the black hole's event horizon. The study of black holes has revealed something unexpected about the nature of reality itself. These objects seem to store information not in their volume, but on their surface area. It's like a hologram, where a two-dimensional surface can contain all the information needed to reconstruct a three-dimensional image. This holographic principle suggests that our three-dimensional experience of space might itself be a kind of projection from information stored on some distant boundary. What's perhaps most striking about black holes is how they represent the ultimate boundary between the known and unknowable. They're places where our most fundamental concepts, space, time, matter, energy, all get pushed to their breaking point. They force us to confront the possibility that reality might be far stranger and more mysterious than our everyday experience suggests. In the end, black holes remind us that the universe doesn't care about our comfort or our need for simple explanations. They exist as cosmic question marks, challenging us to expand our understanding of what's possible. Every time we think we've figured out how reality works, we discover something like Hawking radiation or time dilation that forces us to reconsider everything we thought we knew. Perhaps that's the most beautiful thing about these cosmic mysteries. They keep us humble, reminding us that for all our scientific progress, we're still just beginning to understand the universe we inhabit. The singularity at the heart of a black hole might forever remain beyond our direct observation, but the questions it raises will continue to drive us toward new discoveries, new ways of thinking about space and time, and the fundamental nature of existence itself. The universe holds mysteries that challenge everything we think we know about reality. Black holes contain something so bizarre, so contrary to our everyday experience, that even scientists struggle to describe it properly. At the heart of every black hole lies what we call a singularity, a concept that breaks all the rules we've grown comfortable with. Think about your morning coffee cup. It has a size, a shape, boundaries you can measure. Everything around you follows this same pattern. Your phone, your house, even the tiniest grain of sand, all occupy space in ways we can understand. But singularities don't play by these rules. They represent points where all the matter that once made up a massive star gets crushed down into, well, nothing. Not something incredibly small, but literally nothing, no space at all. The density becomes infinite. Imagine trying to squeeze an entire mountain into a space smaller than the head of a pin, then keep squeezing until there's no space left whatsoever. That's what happens when gravity wins the ultimate battle against matter. The star's core collapses so completely that it disappears from our normal understanding of space and time. What makes this even stranger is that we can't actually see these singularities, even with our most powerful telescopes. They hide behind what scientists call event horizons, the point of no return around black holes. It's like trying to peek behind a curtain that can never be pulled back. We know something extraordinary is happening back there, but we can only observe the effects from the outside. Those effects are pretty dramatic, though. Stars dance around black holes in perfect orbits, sometimes for millions of years. Gas clouds get stretched like taffy as they spiral inward. Light itself bends and twists in impossible ways. All of this cosmic choreography happens because of something we can't see, can't touch, and can't properly imagine. The mathematics tell us that at the singularity, density becomes infinite, while volume becomes zero. These aren't just big numbers or small numbers, they're concepts that push beyond what numbers can actually represent. It's like trying to divide by zero on a calculator, the universe's way of saying the normal rules don't apply here anymore. Time itself behaves differently near these mysterious points. Close to a singularity, time stretches and warps. What seems like minutes to someone falling toward one might appear as hours to an outside observer. The fabric of space-time, that invisible stage where all of cosmic history plays out, gets twisted into shapes our minds can't follow. Perhaps the most unsettling part is that singularities might not be rare. Cosmic oddities, many galaxies, including our own Milky Way, likely have supermassive black holes at their centers. That means singularities, these points where reality breaks down, sit at the hearts of the largest structures in the universe. They're not just cosmic curiosities tucked away in remote corners of space. They're fundamental to how galaxies form and evolve. The paradox runs deeper than just physics, though. Here we have objects, if we can call them that, which exist everywhere and nowhere at the same time. They occupy no space yet, influence everything around them across vast distances. They're points on no map. Yet, they shape the geography of the entire cosmos. Scientists have spent decades trying to understand what really happens at these mysterious points. Some theories suggest that maybe space and time don't actually disappear, but transform into something so different from our normal experience that our current physics can't describe it. Others propose that singularities might be doorways, connections to other parts of the universe, or even other universes entirely. The challenge isn't just mathematical, it's conceptual. How do you think about something that has no size? How do you imagine a place that isn't really a place? It's like trying to picture the color of silence, or the texture of mathematics. Our brains evolved to navigate a world of objects and boundaries, not infinite densities and zero volumes. Yet somehow, these impossible points drive some of the most beautiful phenomena we observe. The spiral arms of galaxies, the jets of energy that shoot across millions of light years, the precise orbits of stars around galactic centers. All of this cosmic architecture exists because of these points that shouldn't, mathematically speaking, be able to exist at all. The story gets even more interesting when we consider that our entire universe might have emerged from a singularity. The Big Bang, that moment when everything we know began, shares many characteristics with what we find at the centers of black holes. Infinite density, zero volume, the breakdown of normal physics. Perhaps understanding these mysterious points could help us understand our own cosmic origins. There's something almost philosophical about wrestling with singularities. They force us to confront the limits of human understanding. We're creatures who like to measure, categorize, and map our world. But singularities exist beyond measurement, outside categories on no possible map. They remind us that reality might be far stranger than our everyday experience suggests. The instruments we build get better every year, allowing us to peer deeper into space and time. We can now detect gravitational waves, ripples in space-time itself, that occur when black holes collide. We can photograph the event horizons of these cosmic monsters, but the singularities themselves remain hidden, like cosmic riddles wrapped in mathematical enigmas. Maybe that's part of their appeal. In an age where we can look up almost any fact instantly, singularities represent pure mystery. They exist in every galaxy, influence every star, yet remain fundamentally unknowable to us. As you drift off to sleep tonight, somewhere out there, countless singularities sit in the hearts of black holes, warping space and time in ways that would seem like magic, if we could witness them up close. They're the universe's way of reminding us that reality is far more mysterious, far more wonderful than anything we could have imagined. Gravity shapes every moment of our existence, from the coffee that settles in your cup to the way your feet connect with the floor each morning. We take it for granted, this invisible hand that orchestrates the cosmic dance around us. The sun holds Earth in its gravitational embrace, while our planet tugs at the moon, creating the rhythmic rise and fall of ocean tides. Most of the time, gravity behaves predictably. It pulls objects toward each other with a force that depends on their mass and distance. The more massive something is, the stronger its gravitational pull becomes. A bowling ball has more gravitational influence than a marble, though both are dwarfed by Earth's mighty pull. But gravity has a darker, more mysterious side. When matter gets compressed into incredibly small spaces, when stars collapse under their own weight, gravity transforms into something almost unrecognizable. It stops following the gentle rules we observe in our daily lives and starts rewriting the very laws of physics. Consider what happens when a massive star, perhaps 20 times heavier than our sun, reaches the end of its life. Nuclear fusion can no longer fight against the star's own gravitational pull. The star collapses catastrophically, crushing all of that enormous mass into a space smaller than a city. The gravitational field becomes so intense that it warps the fabric of space and time itself. This is where things get truly strange. Space, which we think of as empty, flat, unchanging, starts to curve and bend like a stretched rubber sheet. Time, which flows steadily in our experience, begins to slow down and distort. The stronger the gravitational field, the more dramatic these effects become. At the heart of this collapsed star lies something called a singularity. It's a point where all the star's mass gets squeezed into zero volume, creating infinite density. The mathematics breaks down here. Our equations start spitting out impossible answers. It's as if the universe has reached a place where its own rules no longer apply. Around this singularity, there's an invisible boundary called the event horizon. Cross this line and you can never return. Not because there's a wall or barrier, but because space itself becomes so warped that all paths lead inward. Even light, the fastest thing in the universe, gets trapped and pulled inexorably toward the center. The event horizon isn't a physical surface you could touch. It's more like a point of no return in space-time itself. For a black hole with the mass of our sun, this boundary would sit about 3 kilometers from the center. For the supermassive black holes at the centers of galaxies, the event horizon might stretch across distances larger than our entire solar system. What happens inside this boundary challenges everything we think we know about reality. As matter falls toward the singularity, it gets stretched and compressed in ways that seem almost violent. The gravitational forces become so uneven that objects get pulled apart, stretched like taffy, in a process scientists call spaghettification. Time itself behaves strangely near these extreme gravitational fields. If you could somehow watch someone fall into a black hole, you'd see them slow down as they approach the event horizon. Their movements would become more and more sluggish, their image growing dimmer and redder, until they seemed to freeze at the boundary, fading from view. Yet from their perspective, they would continue falling normally, crossing the event horizon in finite time. This time dilation effect happens because gravity literally warps spacetime. The stronger the gravitational field, the slower time moves relative to distant observers. Near a black hole, this effect becomes extreme. A clock sitting just outside the event horizon would tick incredibly slowly compared to one far away from the black hole's influence. The universe contains millions, perhaps billions of these cosmic monsters. They range from stellar mass black holes, formed when individual stars collapse, to supermassive giants lurking at the centers of galaxies. Our own galaxy, the Milky Way, harbors a supermassive black hole called Sagittarius A star, with the mass of 4 million suns packed into a region smaller than Mercury's orbit. We can't see black holes directly, since they trap light itself, but we observe their effects on surrounding matter. Gas and dust spiral inward, heating up and glowing brilliantly before disappearing forever beyond the event horizon. These accretion disks can outshine entire galaxies, creating some of the most luminous objects in the universe. Sometimes, black holes act like cosmic lighthouses, shooting jets of particles at nearly the speed of light from their poles. These jets can extend for thousands of light years, carrying enormous amounts of energy across intergalactic distances. The mechanism behind these jets remains one of astronomy's great puzzles. Black holes also bend light from objects behind them, acting like gravitational lenses. This effect allows us to see distorted, magnified images of distant galaxies that would otherwise be hidden. Einstein predicted this phenomenon decades before we had the technology to observe it. Another confirmation of his theories about gravity and space-time, the mathematics describing black holes lead to some truly mind-bending conclusions. At the singularity, density becomes infinite, volume becomes zero, and the curvature of space-time becomes undefined. These infinities suggest that our current theories, successful as they are, remain incomplete. We need new physics to understand what really happens at the center of a black hole. Some theoretical physicists propose that the singularity might not be a point of infinite density, but rather a region where quantum effects become important. Perhaps matter doesn't collapse to a point, but instead gets crushed to the smallest possible size allowed by quantum mechanics. The true nature of the singularity remains one of physics' deepest mysteries. Black holes might not be the cosmic vacuum cleaners popular culture sometimes portrays them as. If you replaced our sun with a black hole of equal mass, Earth would continue orbiting normally. We'd freeze to death without sunlight, but we wouldn't get sucked in. Black holes only trap objects that venture too close to their event horizons. These objects raise profound questions about the nature of information and reality itself. When matter falls into a black hole, what happens to the information it contained? Does it disappear forever? Or does it somehow get preserved? This information paradox has puzzled physicists for decades and continues to drive research at the intersection of gravity and quantum mechanics. Perhaps most remarkably, black holes aren't perfectly black after all. Quantum effects near the event horizon cause them to emit radiation, slowly evaporating over incomprehensibly long timescales. A black hole with the sun's mass would take longer than the age of the universe to evaporate completely. But given enough time, even the largest black holes will eventually fade away, leaving only empty space behind. The study of these extreme objects pushes us to the very limits of human understanding. They exist at the boundary between the known and unknown, where our most successful theories begin to break down. In contemplating them, we confront both the power and limitations of human knowledge, forever drawn toward mysteries that may never be fully resolved. Space and time behave in ways that would seem impossible in our everyday world. Imagine gravity, so strong that it literally bends the fabric of reality around it. This isn't science fiction. This is what happens near a black hole. The event horizon sits there like an invisible fence in space. You can't see it, you can't touch it, but once you cross it, there's no coming back. It's the ultimate one-way ticket. Nothing that passes through can ever return, not even light itself. What's fascinating is how this boundary plays tricks with time. As you approach the event horizon, time starts to stretch like taffy. Each second becomes longer and longer. From far away, someone watching you would see you slow down more and more until you appear frozen in time, never quite crossing over. But here's where it gets really strange. From your perspective, time feels normal. You'd cross the event horizon without even noticing the moment it happens. Meanwhile, to that distant observer, you'd be stuck there forever, gradually fading away. The mathematics behind this time distortion comes from Einstein's theories. Gravity doesn't just pull on objects, it actually warps the space and time around it. Near a black hole, this warping becomes so extreme that our normal understanding breaks down completely. Think about how we navigate through life using familiar reference points. We know up from down, past from future, here from there. But near the event horizon, these concepts start to lose their meaning. Space curves back on itself in ways that our brains simply weren't designed to comprehend. The singularity at the center of a black hole represents the ultimate mystery. It's a point where density becomes infinite, where the normal laws of physics simply give up. We can calculate what should happen there, but the math produces answers that don't make sense in our everyday world. Scientists have discovered that black holes come in different sizes. Some are just a few times more massive than our Sun, while others contain billions of solar masses. The larger the black hole, the gentler its event horizon. You might actually survive crossing into a supermassive black hole, at least initially. The process that creates these cosmic monsters is surprisingly violent. When massive stars run out of fuel, they collapse catastrophically. In mere seconds, matter that once filled a space larger than Earth gets compressed into a point smaller than a marble. What happens to information that falls into a black hole puzzles physicists to this day. Does it get destroyed forever, or does it somehow survive in a scrambled form? This question touches on fundamental principles about how reality works at its deepest level. Stephen Hawking discovered that black holes aren't perfectly black after all. They emit a faint radiation, slowly evaporating over enormous periods of time. A black hole with the mass of our Sun would take longer than the age of the universe to disappear completely. The radiation that black holes emit is incredibly cold, much colder than the background temperature of space itself. Paradoxically, smaller black holes are actually hotter than larger ones. It's another example of how these objects defy our everyday intuitions. Near the event horizon, space itself gets dragged around, like honey stirred with a spoon. This effect, called frame dragging, means that nothing can remain perfectly still relative to distant stars. Everything gets swept along in the black hole's gravitational whirlpool. If you could somehow survive near a black hole, you'd witness the entire future history of the universe unfold before your eyes. Due to time dilation, you'd see distant galaxies evolve at incredible speed, stars being born and dying in what seems like moments. The event horizon acts like a cosmic sensor, hiding the singularity from the outside universe. This cosmic censorship principle suggests that nature has built-in mechanisms to prevent us from directly observing infinities and paradoxes. Some scientists speculate that the intense conditions near black holes might create shortcuts through space and time. These hypothetical wormholes could theoretically connect distant parts of the universe, though whether they could actually exist remains deeply uncertain. The tidal forces near smaller black holes would stretch your body like a noodle, a process scientists colorfully call spaghettification. Your feet would experience much stronger gravity than your head, pulling you apart long before you reach the event horizon. We've recently captured the first images of black holes using networks of telescopes spanning the entire Earth. These pictures show the glowing disk of material spiraling into the black hole, heating up to billions of degrees as it falls. The matter falling into a black hole doesn't disappear quietly. It forms an accretion disk, spinning faster and faster as it approaches the event horizon. The friction in this disk generates some of the brightest objects in the universe, visible from billions of light years away. Black holes might play a crucial role in galaxy formation. The supermassive black holes, found at the centers of most galaxies, seem to regulate how quickly stars can form throughout their host galaxies, acting like cosmic thermostats. Perhaps most remarkably, black holes connect the largest scales of the universe with the smallest. They bring together Einstein's theory of gravity with quantum mechanics in ways we still don't fully understand, promising new insights into the fundamental nature of reality itself. Light carries the secrets of distant worlds to our eyes every single night. When we gaze upward, we're actually looking back in time, seeing photons that began their journey millions of years ago. These tiny messengers of energy move at the fastest possible speed through space, yet something in our universe can capture them completely. Gravity shapes everything we know. It keeps our feet planted firmly on the ground, guides planets in their endless orbits around stars, and holds entire galaxies together in cosmic dance. The strength of this invisible force depends on how much mass something contains and how close you are to it. More mass means stronger pull. Get closer, and that pull becomes even more intense. Black holes represent gravity taken to its absolute extreme. These cosmic monsters form when massive stars collapse under their own weight, creating regions where gravity becomes so powerful that it bends the very fabric of space and time. Think of space like a stretched rubber sheet. Place a heavy bowling ball in the center, and you'll see how it creates a deep well that curves the surface around it. Near a black hole, this curving becomes so extreme that it creates something called an event horizon. This invisible boundary marks the point of no return, where the gravitational pull becomes stronger than anything else in the universe, even light itself. Cross this line, and there's no coming back. What happens to light as it approaches this cosmic trap is both beautiful and terrifying. The intense gravity begins to stretch the light waves, pulling them toward longer, redder wavelengths. This process, known as gravitational redshift, occurs because the black hole's immense mass warps space-time so dramatically that it changes how light behaves. As photons spiral closer to the event horizon, they face an impossible struggle. These particles, which normally travel in straight lines across the cosmos, find their paths bending more and more sharply inward. Space itself becomes so curved that there are no longer any paths leading away from the black hole's center. Imagine trying to climb out of a well whose walls keep getting steeper and more slippery the deeper you go. Eventually, the sides become so steep that escape becomes impossible, no matter how hard you try. Light faces a similar predicament near the event horizon. The curvature of space-time creates walls so steep that even traveling at the speed of light isn't fast enough to climb out. Once light crosses the event horizon, it vanishes from our universe forever. The photons continue falling inward toward the singularity, that mysterious point at the black hole's center, where gravity becomes infinite and the normal laws of physics break down completely. These particles join everything else that has ever fallen past the point of no return, compressed into a space smaller than an atom. This is why we call them black holes. They emit no light, because no light can escape from them. They appear as dark voids against a star-filled background of space, cosmic shadows that reveal themselves only by how they affect everything around them. Matter spiraling into a black hole heats up and glows brightly, creating swirling disks of superheated gas that shine like cosmic lighthouses. The trapping of light creates one of the most profound mysteries in modern science. When information crosses the event horizon, it becomes forever hidden from the rest of the universe. We can never know what happens inside a black hole because no signal can ever reach us from beyond that boundary. It's as if these objects create holes not just in space, but in knowledge itself. Scientists call this the information paradox. Does the information about everything that falls into a black hole get destroyed forever, or does it somehow remain encoded on the event horizon's surface, like a cosmic library that we can never read? This question touches the very foundations of physics and our understanding of reality. The event horizon acts like a one-way mirror in reverse. We can see things falling toward it from our perspective, but once they cross over, they vanish completely. Time dilation near the black hole creates another strange effect. To an outside observer, objects approaching the event horizon appear to slow down and freeze at the boundary, their light becoming redder and dimmer until it fades away entirely. Meanwhile, from the perspective of someone falling into the black hole, time flows normally. They would pass through the event horizon without feeling anything special happen at that moment. The real danger comes from tidal forces, the difference in gravitational pull between their head and feet, which would eventually stretch them into a long, thin shape. Black holes come in different sizes, from stellar mass holes a few times heavier than our sun, to supermassive giants containing billions of times the sun's mass. These monsters lurk at the centers of galaxies, including our own Milky Way. The larger the black hole, the gentler its tidal forces at the event horizon, meaning you could potentially cross the boundary of a supermassive black hole without immediately noticing. The mathematics describing black holes emerged from Einstein's theory of general relativity, decades before anyone found evidence these objects actually exist. The equations predicted something so extreme that even Einstein himself doubted whether nature would allow such things to form. Yet observations have confirmed that black holes are common throughout the universe. We detect them by watching how they influence nearby matter and light. Stars orbiting invisible companions reveal black holes through their gravitational dance. Matter falling into these cosmic drains creates some of the brightest objects in the universe as it heats up and accelerates to incredible speeds. The recent direct imaging of black hole event horizons has given us our first actual pictures of these cosmic boundaries. The images show glowing rings of hot gas surrounding dark centers, visual proof of regions where light itself cannot escape. These photographs represent the shadows cast by the event horizons against the bright backgrounds of superheated matter. Quantum mechanics adds another layer of mystery to black holes. According to quantum theory, black holes should eventually evaporate by emitting radiation, slowly shrinking over vast periods of time. This process would take longer than the current age of the universe for most black holes, but it raises questions about what happens to all that trapped information when the black hole finally disappears. The study of black holes pushes us to the very limits of human understanding. These objects exist at the intersection of our two most successful theories, general relativity and quantum mechanics, revealing places where these frameworks don't quite fit together. They represent natural laboratories for testing the most extreme predictions of physics. Perhaps what makes black holes most fascinating is how they challenge our intuition about the universe. We're accustomed to thinking that everything has an escape route, that nothing is truly permanent or unchangeable. Yet here are objects that violate this assumption completely, creating permanent prisons for light and matter. The trapped photons serve as reminders of the universe's vast mysteries. Each one represents a story we'll never hear, information about distant places and times that has been locked away forever. They embody the fundamental limits of knowledge and observation that define our existence as conscious beings trying to understand the cosmos. In contemplating light's fate near black holes, we confront questions that go beyond physics into philosophy. What does it mean for information to be truly lost? How do we reconcile our desire to understand everything with the existence of places that are fundamentally unknowable? These cosmic prisons for light force us to accept that some mysteries may remain forever beyond our reach. When we think about time in our daily lives, it feels like this steady, reliable force that just keeps moving forward. 1 second follows another, minutes turn into hours, and days blend into years. We set our clocks, make our schedules, and trust that time will behave exactly as we expect it to. But the universe has other plans for time, especially in the most extreme places we can imagine. Out in the depths of space, where gravity becomes so intense it warps reality itself, time stops being the predictable companion we know. Near these cosmic monsters called black holes, time starts to play by completely different rules. The very fabric of space and time gets stretched and twisted like taffy, pulled by gravitational forces so powerful they defy our everyday experience. Picture yourself drifting closer to one of these gravitational giants. As you approach what scientists call the event horizon, that invisible boundary around a black hole, something extraordinary begins to happen. Time itself starts to slow down around you. The stars in the distance, which normally twinkle at their usual pace, begin to appear sluggish. Their light gets stretched, making them flicker more slowly, more faintly. From your perspective near this cosmic edge, the entire universe seems to be moving in slow motion. Distant galaxies crawl across the sky, like snails. Everything that should be happening quickly happens at a crawl. It's as if someone has pressed a slow motion button on the entire cosmos. But here's where it gets really strange. To you, floating near that event horizon, everything about your own experience feels completely normal. Your thoughts move at their usual speed, your heartbeat maintains its rhythm, your watch ticks away second by second, just like it always has. You don't feel slow at all. Meanwhile, if someone could watch you from far away, safe from the black hole's influence, you would appear to be moving incredibly slowly. Every gesture you make, every step you take, would seem to stretch out over what feels like hours to that distant observer. The closer you drift to that invisible boundary, the slower you appear to them, until, eventually you seem to freeze completely. This mind-bending effect has a name: time dilation. It's one of those concepts that sounds like science fiction but represents the very real way gravity affects time. The stronger the gravitational field, the more time gets stretched and distorted. Near a black hole, where gravity reaches its most extreme levels, time dilation becomes so pronounced that it creates these seemingly impossible scenarios. If you actually crossed that event horizon, something even more peculiar would happen. From the perspective of that distant observer, you would appear to stop completely, frozen at that boundary forever. But your own experience would be entirely different. You would continue falling, experiencing time at what feels like a normal pace, while the universe outside seems to speed up around you. As you fell deeper into the black hole, the stars and galaxies you left behind would appear to accelerate, racing through time faster and faster. Millions of years of cosmic evolution might flash by in what feels like moments to you. You become isolated in your own pocket of time, disconnected from the temporal rhythm of the rest of the universe. Light behaves in a similar way near these gravitational monsters. As photons travel closer to a black hole, their paths get bent and twisted by the intense gravity. Eventually, once they cross that event horizon, they become trapped forever. Unable to escape back to the outside universe, time follows this same pattern, getting bent and distorted, until it no longer operates according to the rules we understand. At the very center of a black hole lies something called a singularity. This represents a point where the normal laws of physics completely break down. Space and time become so warped, so infinitely curved, that they lose all meaning in the way we normally think about them. Time stops being a simple progression from past to present to future, and becomes something far stranger. The singularity challenges our most basic assumptions about reality. In our everyday world, time flows in one clear direction, helping us organize cause and effect, memory and anticipation. But in these extreme cosmic environments, time becomes fluid, changeable, no longer the reliable constant we depend on. This revelation transforms our understanding of what time actually is. Rather than being some universal clock ticking away in the background of reality, time turns out to be woven directly into the fabric of space itself. When space gets warped by gravity, time warps right along with it. They're not separate things, but part of a unified whole that scientists call spacetime. Black holes serve as natural laboratories for studying these extreme effects. They show us that time isn't fixed or absolute, but flexible and relative. What counts as simultaneous, what counts as before or after, depends entirely on where you are and how fast you're moving through the gravitational landscape of the universe. This flexibility of time extends beyond black holes too. Even here on Earth, time moves slightly slower at sea level than it does on a mountaintop, because gravity is just a tiny bit stronger down lower. The difference is minuscule, measurable only with extremely precise instruments, but it's real. GPS satellites have to account for these tiny time differences to give us accurate directions. The more we study these temporal effects, the more we realize that time is far stranger and more wonderful than our intuitions suggest. It's not just a backdrop against which events unfold, but an active participant in the cosmic dance. Gravity doesn't just pull on matter, it pulls on time itself, stretching moments, compressing durations, creating pockets where causality itself becomes ambiguous. These discoveries force us to reconsider some of our deepest philosophical questions about existence. If time can slow down, speed up, and even stop under the right conditions, what does that mean for our understanding of permanence and change? What happens to the idea of a universal now, a moment that everyone in the universe shares simultaneously? The answer seems to be that there is no universal now. Time is local, personal, dependent on your particular journey through the cosmos. Your now and someone else's now might be completely different moments, depending on how you've each been affected by gravity and motion throughout your lives. This relativity of time also raises fascinating questions about consciousness and experience. If time can be stretched or compressed, what happens to the stream of thoughts and sensations that make up our inner lives? Would thoughts themselves slow down in a strong gravitational field? Or would consciousness somehow remain constant while the physical world around it distorted? Scientists continue to probe these questions using increasingly sophisticated tools and theories. They've detected gravitational waves, ripples in spacetime itself, that provide new ways to study how gravity affects the flow of time. They've observed light from distant stars getting redshifted as it climbs out of gravitational wells, carrying information about how time runs differently in various cosmic environments. Each new discovery adds another piece to the puzzle of understanding time's true nature. We've learned that time had a beginning with the Big Bang, that it might have multiple dimensions we can't perceive directly, and that it might even be quantized at the smallest scales, made up of discrete units rather than flowing smoothly. The study of time near black holes also connects to broader questions about the ultimate fate of information in the universe. If something falls into a black hole, does the information that describes it get destroyed forever, or is it somehow preserved in a form we don't yet understand? This information paradox represents one of the deepest unsolved problems in physics. As we push the boundaries of our understanding, we keep discovering that reality operates according to principles far more strange and beautiful than we initially imagined. Time, that most familiar aspect of our existence, turns out to be one of the most mysterious and flexible features of the cosmos. Every galaxy in our universe contains a cosmic engine, spinning silently at its center, invisible yet impossibly powerful. These supermassive black holes aren't just empty voids, they're the architects of everything we see around them. When we look up at the night sky, we're seeing the result of billions of years of their quiet influence. Our own Milky Way harbors one of these giants, called Sagittarius A star. It weighs about 4 million times more than our Sun, yet we've never actually seen it directly. What we do see are the stars dancing around it, whipping through space at speeds that would make your head spin. These stellar performers trace perfect ellipses, like cosmic ballet dancers, all because of something we can't even observe. The strange thing about black holes is how they reveal themselves, through absence rather than presence. We know they're there because of what they do to everything else. Stars that venture too close get stretched and pulled, their light shifting colors as gravity plays tricks with time itself. It's like watching shadows on a wall and trying to figure out what's casting them. Think about how peculiar this is. The most important object in our galaxy, the thing that holds it all together, remains completely hidden from view. We've built telescopes that can see galaxies billions of light years away, but the heart of our own cosmic home stays stubbornly invisible. It's humbling, really, how the universe keeps its biggest secrets right under our noses. These black holes didn't start out massive, they grew that way over time. In the early days of galaxy formation, they began as smaller objects, maybe just a few times heavier than our Sun, but they had appetites, and space provided plenty to feast on. Gas clouds, unlucky stars, entire solar systems, all eventually found their way down into these gravitational wells. As matter spirals into a black hole, something remarkable happens. The material heats up, getting hotter than the surface of any star. This creates what astronomers call an accretion disk, a swirling maelstrom of superheated gas that glows brighter than anything else in the galaxy. Sometimes these disks shoot jets of energy thousands of light years into space, like cosmic lighthouses broadcasting their presence across the universe. The relationship between a galaxy and its central black hole is surprisingly intimate. They seem to grow together, almost like dance partners keeping time with each other. When the black hole feeds and grows larger, the galaxy around it changes too. When the galaxy collects more stars and gas, the black hole benefits as well. It's a partnership that's lasted for billions of years, but this relationship has a dark side. Black holes can be galaxy killers as well as galaxy builders. When they feed too aggressively, they heat up all the gas around them, preventing new stars from forming. Entire regions of space become stellar deserts, empty of the raw materials needed for star birth. The black hole, in essence, can eat itself out of house and home. Scientists have discovered that almost every large galaxy has one of these monsters at its center. It seems to be a universal rule, like gravity or thermodynamics. You can't have a proper galaxy without a supermassive black hole calling the shots. This makes us wonder, which came first, the galaxy or the black hole? It's a cosmic chicken and egg problem that keeps astronomers busy. The scale of these objects defies our everyday understanding. Sagittarius A star, sitting about 26,000 light-years from Earth, has an event horizon, the point of no return, that's roughly the size of Mercury's orbit around the Sun. If you could somehow approach it, time itself would start behaving strangely. Minutes would stretch into hours, hours into days, as gravity warped the very fabric of space-time. What's perhaps most fascinating is how these invisible giants communicate across space. When two galaxies collide, their central black holes eventually find each other, spiraling closer and closer over millions of years. When they finally merge, they create ripples in space-time itself, gravitational waves that we can now detect with sensitive instruments here on Earth. Each galaxy represents a story billions of years in the making. The Andromeda Galaxy, our nearest large neighbor, has its own supermassive black hole, probably even larger than ours. In about 4 billion years, when Andromeda and the Milky Way collide, these two giants will begin their own slow dance toward merger. The resulting galaxy will have a new heart, one born from the marriage of two cosmic titans. Black holes challenge our basic understanding of physics. They represent places where our normal rules break down completely. At their centers, density becomes infinite, time stops, and space itself gets twisted into impossible shapes. They're like cosmic question marks, reminding us that the universe still holds mysteries we may never solve. The energy output from feeding black holes can be tremendous. Some of the brightest objects in the universe, called quasars, are actually distant galaxies whose central black holes are having particularly large meals. These cosmic beacons can outshine entire galaxies, sending their light across billions of light years to reach our telescopes. They're like cosmic lighthouses, marking the locations of the most active galactic hearts. We live in an age where we can actually photograph the shadows of black holes. Recent technological achievements have allowed us to image the event horizons of these objects, seeing the dark silhouettes they cast against the glowing gas around them. It's like finally seeing the face of something that's been hiding behind a mask for centuries. The magnetic fields around black holes can be incredibly powerful, millions of times stronger than anything we experience on Earth. These fields help channel the jets of material that shoot out from the accretion disks, creating some of the most spectacular light shows in the universe. The interplay between gravity, magnetism, and radiation creates a complex cosmic ecosystem. As we drift off to sleep tonight, we're passengers on a planet orbiting a star that's orbiting a supermassive black hole. We're all part of this grand galactic carousel, spinning through space at hundreds of kilometers per second. The invisible heart of our galaxy keeps us all in line, a hidden conductor orchestrating a symphony of billions of stars. Perhaps there's something poetic about how the most important things in the universe remain hidden from direct view. Love, consciousness, the meaning of existence, the hearts of galaxies, all invisible, yet undeniably real. We know they exist by their effects, by the way they shape everything around them, by the patterns they create in the visible world. The universe operates through cycles that most of us never really consider. Stars begin their lives in enormous clouds of gas and dust, these stellar nurseries where gravity slowly pulls material together over millions of years. Nuclear fusion ignites in their cores, creating the energy that makes them shine. This process can continue for billions of years depending on the star's mass. The more massive a star is, the faster it burns through its fuel, almost like a cosmic contradiction, where having more means lasting less. When a star exhausts its nuclear fuel, something remarkable happens. The outward pressure from fusion reactions can no longer counteract the star's own gravitational pull. Gravity wins this cosmic tug of war, and the star begins collapsing inward. For stars similar to our Sun, this collapse creates white, incredibly dense objects about the size of Earth but containing most of the original star's mass. A teaspoon of white dwarf material would weigh as much as a car. More massive stars face a different fate entirely. Their collapse triggers one of the most violent events in the universe, a supernova explosion. These explosions are so powerful they can briefly outshine entire galaxies containing billions of stars. The energy released in a single supernova exceeds what our Sun will produce over its entire 10 billion-year lifetime. It's almost impossible to comprehend such scales of energy, yet these events happen regularly throughout the cosmos. After a supernova, what remains depends on the original star's mass. Some leave behind neutron stars, objects so dense that a sugar cube-sized piece would weigh as much as Mount Everest. Neutron stars spin incredibly fast, some rotating hundreds of times per second. Their magnetic fields are trillions of times stronger than Earth's, powerful enough to strip electrons from atoms thousands of kilometers away. The most massive stars create something even more extreme during their collapse. They form black holes, regions where gravity becomes so intense that nothing can escape, not even light itself. The boundary around a black hole is called the event horizon, and crossing it represents a point of no return. Time itself behaves strangely near black holes, slowing down relative to distant observers due to gravity's effect on space-time. Black holes challenge our everyday understanding of reality. At their centers lies what physicists call a singularity, where the normal laws of physics break down completely. Matter gets compressed to infinite density, and space-time curvature becomes infinite. These concepts push the boundaries of human comprehension, reminding us how much mystery still exists in our universe. Yet black holes aren't just cosmic destroyers, they play crucial roles in galaxy formation and evolution. Most galaxies, including our own Milky Way, contain supermassive black holes at their centers. These giants can contain millions or billions of times the mass of our Sun. They influence star formation across entire galaxies, regulating how quickly new stars are born through their gravitational effects and energy output. The relationship between destruction and creation appears throughout cosmic evolution. When massive stars explode as supernovas, they scatter heavy elements across space. These elements, forged in stellar cores through nuclear fusion, become the building blocks for rocky planets and eventually life itself. Carbon in our bodies, oxygen we breathe, iron in our blood, all originated in stellar cores and were distributed by stellar explosions. This cosmic recycling process has continued for billions of years. Early stars contained only hydrogen and helium, the simplest elements created after the Big Bang. Through successive generations of stellar birth, life and death, the universe has gradually enriched itself with heavier elements. We are quite literally made of star stuff, connected to the cosmos in the most fundamental way possible. Galaxies themselves follow similar patterns of birth, evolution, and eventual demise. They form through gravitational collapse of dark matter and gas, merge with other galaxies, and slowly exhaust their star-forming material. Our Milky Way will collide with the Andromeda Galaxy in about 4 billion years, creating a new larger galaxy through this cosmic merger. The universe's expansion adds another layer to these cycles. Space itself is stretching, carrying galaxies away from each other at increasing speeds. This expansion affects how structures form and evolve over cosmic time. Eventually, if expansion continues accelerating, galaxies will become isolated islands in an increasingly empty universe. Even black holes, seemingly permanent fixtures of the cosmos, slowly evaporate through a process called Hawking radiation. This quantum mechanical effect causes black holes to emit particles and gradually lose mass over incredibly long timescales. The largest black holes will take longer than the current age of the universe multiplied by trillions of times to completely evaporate. These vast timescales dwarf human experience and challenge our intuitions about permanence. What seems eternal from our perspective represents brief moments in cosmic time. Mountain ranges rise and erode, continents drift across Earth's surface, our solar system orbits the galaxy's center, and the galaxy itself moves through space as part of larger cosmic structures. Understanding these processes reveals something profound about existence itself. Every atom in our bodies has likely been part of multiple stars throughout cosmic history. We are temporary arrangements of matter that has existed for nearly 14 billion years and will continue existing Long after our individual patterns dissolve, there's something both humbling and comforting about this perspective, connecting us to the grandest scales of space and time, while highlighting the preciousness of our brief, conscious moment within this vast cosmic story. The sensation of falling lies somewhere deep in our memory, doesn't it? That moment when the floor disappears beneath us, when our stomach drops, when gravity suddenly reminds us who's really in charge. Every human being knows this feeling, this brief dance with weightlessness before the inevitable pull downward takes hold. But gravity, as familiar as it seems, operates by rules that would sound like fiction if we didn't know them to be true. Near massive objects, something remarkable happens to the very fabric of reality. Space bends, time stretches, and the simple act of falling becomes something far more complex than we could ever imagine. Consider what happens when you approach a black hole. These cosmic monsters pack so much mass into such a small space that they create gravitational fields of unimaginable strength. The closer you get to one, the more dramatically time itself begins to behave in ways that defy our everyday understanding. From your perspective, falling toward a black hole would feel surprisingly normal at first. You'd experience weightlessness, much like an astronaut in orbit. Time would seem to tick by at its usual pace. You wouldn't feel yourself slowing down or speeding up in any unusual way. Your watch would keep perfect time, at least from your point of view. But here's where things get strange. If someone could watch you fall from a safe distance, they would see something entirely different. To them, your descent would appear to slow down dramatically as you approach the event horizon. The event horizon, that invisible boundary around the black hole where escape becomes impossible, acts like a one-way door in space-time. This observer would watch you fall slower and slower until eventually you would appear to freeze completely at the edge of the event horizon. From their perspective, you would remain there forever, suspended in time, never quite crossing that final threshold. Your image would grow fainter and redder as the light from your body gets stretched by the immense gravitational field, but you would never disappear completely. This isn't some optical illusion or trick of perception. This is time dilation, one of the most profound consequences of Einstein's theory of relativity. Time literally runs at different rates depending on how strong the gravitational field is around you. The stronger the gravity, the slower time moves, relative to areas with weaker gravitational pull. Think about it for a moment. Two people can experience the same event, the same fall, the same moment in space, and yet time passes differently for each of them. It challenges everything we think we know about the nature of reality, about what it means for something to happen at a specific time. This stretching of time near black holes creates what physicists call gravitational time dilation. Clocks run slower in stronger gravitational fields. This effect happens everywhere, even here on Earth. But it's so small we don't notice it in our daily lives. GPS satellites actually have to account for this effect because they orbit high above Earth, where gravity is slightly weaker, causing their clocks to run faster than clocks on the surface. But near a black hole, this effect becomes extreme. The gravitational field is so intense that time can slow to a crawl compared to the rest of the universe. What takes seconds from your perspective might appear to take years, decades, or even centuries to an outside observer. There's something almost poetic about this cosmic dance between time and gravity. The universe seems to have built-in mechanisms that prevent us from witnessing certain events. As you fall past the event horizon, you become forever separated from the outside universe, not just in space, but in time itself. Once you cross that threshold, no information about your experience can ever escape to tell the tale. Light itself cannot climb out of the gravitational well you've fallen into. You become isolated from the rest of reality, trapped in a pocket of space-time that follows its own rules. From your perspective inside the event horizon, you would continue falling toward the center of the black hole, toward what physicists call the singularity. This is a point where our current understanding of physics breaks down completely. Density becomes infinite, the curvature of space-time becomes infinite, and the normal laws that govern reality cease to make sense. But even more strange is what happens to your body as you fall. The gravitational pull at your feet would be significantly stronger than the pull at your head, creating what scientists call tidal forces. These forces would stretch you vertically while compressing you horizontally, an effect that has been nicknamed spaghettification. For smaller black holes, these tidal forces would tear you apart long before you reach the event horizon. But for supermassive black holes, the ones millions or billions of times more massive than our Sun, you might actually survive crossing the event horizon intact, only to be stretched apart closer to the singularity. The fact that black holes can have such different effects, depending on their size, reveals something beautiful about the mathematics of gravity. The same fundamental force that keeps our feet on the ground and our planet in orbit around the Sun can also create these cosmic monsters that warp space-time beyond recognition. What's perhaps most unsettling is that from your perspective, falling into a black hole might not feel dramatic at all. You wouldn't necessarily realize you had crossed the point of no return. Space would look curved and distorted around you, and you might see strange optical effects as light from the outside universe gets bent and twisted by the extreme gravity. You might even see the entire future history of the universe flash before your eyes, compressed into the final moments before you reach the singularity. Light from the outside universe would be blue-shifted and accelerated, potentially allowing you to witness eons of cosmic evolution in what feels like minutes or seconds. This paradox of falling forever without moving reveals something profound about the nature of time itself. Time isn't the constant, universal backdrop we once thought it was. It's fluid, malleable, intimately connected to the structure of space and the presence of matter and energy. Every massive object in the universe creates its own time zone, its own rate at which events unfold. Earth creates a slight time dilation compared to empty space. The Sun creates a stronger effect. White dwarf stars, neutron stars, and finally black holes create increasingly dramatic distortions in the flow of time. Perhaps there's something humbling about this. Our human experience of time, our sense that moments tick by at a steady, predictable rate, is just one perspective among many possible perspectives in the universe. Somewhere out there, in the strong gravitational field of a massive object, time is crawling by at a pace we can barely imagine. And somewhere else, in the weak gravitational field of intergalactic space, time flows faster than it does here on Earth. The universe is full of these different temporal neighborhoods, each operating according to its own clock, each offering its own perspective on when events occur. The study of black holes has taught us that the universe is far stranger and more beautiful than we ever imagined. These objects represent the ultimate triumph of gravity over all other forces, places where matter has collapsed so completely that it punches holes in the fabric of space-time itself. Yet even in their strangeness, black holes follow rules. They obey the laws of physics, even if those laws lead to consequences that challenge our intuition. They remind us that the universe operates on principles that extend far beyond our everyday experience, principles that can create phenomena that seem almost magical in their impossibility. Everything around us feels so permanent, so solid. The ground beneath our feet, the walls of our homes, even the air we breathe. We live in a world where things have shape, where objects maintain their form from one moment to the next. A rock stays a rock, water remains water, and the basic building blocks of reality seem to follow predictable patterns. But imagine if you could peer into the most extreme places in our universe. Places where everything we think we know about the nature of reality gets turned completely upside down. Deep in the heart of black holes, something extraordinary happens. Matter, the very stuff that makes up everything we can see and touch, undergoes a transformation so complete that it essentially forgets what it used to be. Think about what matter actually is for a moment. At its core, it's just atoms, tiny particles made of protons, neutrons, and electrons, all dancing around each other in incredibly organized ways. These atoms link up to form molecules, and those molecules create everything from the simplest gases to the most complex structures we know. Each type of matter has its own personality, its own set of rules, its own way of interacting with the world. Iron behaves like iron, carbon acts like carbon, hydrogen follows its own patterns. For billions of years, these elements have maintained their identities throughout the cosmos. They've traveled across vast distances, been part of countless stars, formed planets, and even become part of living beings like us. Through all of these journeys, they've kept their essential characteristics intact. But there's something in space that can change all of that completely. Black holes represent perhaps the most violent, most extreme environments that exist anywhere in the universe. When matter gets too close to one of these cosmic monsters, it begins a journey that will fundamentally alter its very existence. The process starts gradually. As objects approach a black hole, they feel the pull of gravity, getting stronger and stronger. But here's where things get really strange. The gravitational force doesn't pull evenly on everything. The parts of an object that are closest to the black hole experience much stronger forces than the parts that are farther away. This creates what scientists call tidal forces. Just like how the moon's gravity creates tides in our oceans, these tidal forces around black holes are incredibly powerful. They stretch and pull at anything that gets too close. If you could somehow watch a spacecraft falling into a black hole, you'd see it getting longer and thinner, almost like it was being pulled apart, like taffy. Scientists have given this process a wonderfully descriptive name. They call it spaghettification. The image is pretty accurate too. Imagine taking a piece of spaghetti and pulling on both ends until it gets thinner and thinner. That's essentially what happens to matter as it falls toward the center of a black hole. But the stretching is just the beginning of the story. As matter continues its journey inward, it crosses what's called the event horizon. This is basically the point of no return. Once something crosses this invisible boundary, there's no coming back. It's committed to falling all the way to the center of the black hole. And at that center lies something that challenges our understanding of reality itself. Scientists call it a singularity, a point where all the matter that has fallen into the black hole gets compressed into an infinitely small space. The very concept seems impossible to our everyday minds. How can something have infinite density? How can all that matter, potentially the mass of millions of stars, exist in a space smaller than a single atom? At the singularity, the normal rules that govern matter simply break down. The atoms that once made up planets, stars, and galaxies lose their individual identities. Protons, neutrons, electrons, all the fundamental particles that we think of as the building blocks of reality get crushed together so completely that they can no longer exist as separate entities. It's almost as if the matter develops a kind of cosmic amnesia. The iron atoms that once formed the core of a distant planet can no longer remember being iron. The hydrogen that once fueled a massive star forgets its role in nuclear fusion. Everything becomes part of something new, something that exists in a state we can barely comprehend. This transformation represents one of the most profound mysteries in all of physics. We live in a universe where information is supposed to be conserved. The idea is that you should always be able to trace back the history of any particle, figure out where it came from and what it used to be. But at the singularity of a black hole, that history seems to get completely erased. Think about a book being thrown into a fire. Even though the book gets destroyed, the information it contained doesn't really disappear. It gets converted into heat and light and smoke, and theoretically, if you had perfect knowledge of every particle involved, you could reconstruct what the book said. But a black hole seems to do something different. It appears to take that information and hide it away so completely that it might as well not exist anymore. This creates what physicists call the information paradox. It's one of the biggest unsolved problems in modern science. Does the information about all that matter really get destroyed? Or is it somehow preserved in a form we don't understand yet? The question has kept some of the brightest minds in physics busy for decades. But there's another side to this story that's equally fascinating. While black holes seem to destroy matter in the most complete way possible, they also play a crucial role in creating new structures throughout the universe. When matter falls into a black hole, it doesn't just disappear quietly. The process is incredibly violent and energetic. As gas and dust spiral inward, they heat up to tremendous temperatures, sometimes millions of degrees. This superheated material glows brightly, creating some of the most luminous objects in the entire universe. These accretion disks around black holes can outshine entire galaxies, sending jets of particles shooting out at nearly the speed of light. These jets carry energy and matter far out into space, where they can trigger the formation of new stars and influence the evolution of entire galaxies. In a sense, black holes act like cosmic recycling centers. They take old matter, break it down completely, and then redistribute energy and material in ways that help create new cosmic structures. There's something almost poetic about this process. The same forces that can completely erase the identity of matter also help nurture the birth of new stars, new planets, and potentially new forms of life. Destruction and creation become two sides of the same cosmic coin. This cycle has been going on for billions of years throughout the universe. The atoms in your body have likely been through countless transformations. They might have been part of ancient stars that lived and died long before our solar system even existed. Some of them might have even had close encounters with black holes, surviving journeys that brought them to the very edge of oblivion. The carbon in your muscles, the iron in your blood, the calcium in your bones. All of these elements were forged in the hearts of stars and scattered through space when those stars reached the end of their lives. They've traveled unimaginable distances and experienced conditions that would seem impossible by earthly standards. And yet here they are, organized into the complex patterns that make up a living, thinking being. Matter that has journeyed through the cosmos for eons, that has witnessed the birth and death of stars, that has survived the violent expansion of the early universe, but somehow found its way into the intricate structures that allow you to contemplate your own existence. This perspective can be both humbling and comforting. On one hand, it reminds us how small we are in the grand scheme of the universe. We're made of the same basic ingredients as the most distant galaxies and the most exotic black holes. On the other hand, it suggests that we're intimately connected to everything else that exists. The matter that forgets its identity in black holes isn't really lost forever. Thanks to a phenomenon discovered by physicist Stephen Hawking, black holes actually evaporate over extremely long periods of time. They emit radiation that carries away their mass bit by bit, until eventually, even the most massive black holes completely disappear. This Hawking radiation represents yet another transformation of matter and energy. The information that seemed to be lost forever might actually find its way back into the universe, though in a form so scrambled and transformed that we can barely recognize it. It's like cosmic recycling taken to the ultimate extreme. The timescales involved are almost incomprehensible, though. A black hole with the mass of our sun would take longer to evaporate than the current age of the universe multiplied by trillions and trillions. By the time the largest black holes finally disappear, the universe will be a cold, dark, and nearly empty place, with temperatures just barely above absolute zero. But even in that distant future, the cycle of transformation will continue. The energy released by evaporating black holes will create new particles, new possibilities for matter to organize itself in novel ways. The universe might look completely different, but the fundamental process of matter changing from one form to another will persist. These extreme transformations challenge us to think about identity and permanence in new ways. If matter can forget what it used to be so completely, what does that say about the nature of existence itself? Are the things we think of as permanent and solid really just temporary arrangements of more fundamental ingredients? In some ways, black holes represent the ultimate test of our understanding of reality. They push the laws of physics to their absolute limits and beyond. They force us to confront questions about the nature of space, time, information, and matter that we're still struggling to answer. And perhaps that's exactly as it should be. The universe has spent over 13 billion years creating structures of incredible complexity and beauty. From the simplest atoms to the most intricate galaxies, matter has organized itself in ways that continue to surprise and inspire us. The fact that there are still profound mysteries, still places where our understanding breaks down completely, suggests that there are always new discoveries waiting to be made. The universe has this peculiar habit of hiding its deepest secrets in the strangest places. When you think about the edge of a black hole, you might imagine absolute darkness, complete silence, the end of everything. But reality, as it often does, tells a more fascinating story. These cosmic monsters, these gravitational wells so deep that light itself cannot climb out, they're actually buzzing with activity at their very borders. Picture floating, just outside that invisible line we call the event horizon. You're suspended between two completely different versions of reality. On your side, space and time still behave like old, familiar friends. They follow rules, they make sense, they connect to everything we think we know about physics. But one tiny step forward, past that boundary, and you cross into a realm where gravity becomes king, where it overpowers every other force in the universe. What makes this boundary so remarkable isn't just the gravity though, it's the whispers. Quantum whispers that emerge from what looks like empty space. The thing is, empty space isn't really empty at all. It's alive, constantly stirring with the smallest possible movements, the tiniest fluctuations that quantum mechanics allows. We live in a universe where two magnificent theories explain almost everything we see. Einstein's general relativity paints the grand picture, the sweeping curves of spacetime, the dance of planets and stars, the architecture of the cosmos itself. Then there's quantum mechanics, the rulebook for the impossibly small, the world of particles and energy, where everything becomes probability and uncertainty. Each theory works beautifully in its own neighborhood. Relativity governs the massive, the cosmic, the slow and stately waltz of galaxies. Quantum mechanics rules the tiny, the fast, the chaotic jitter of atoms and subatomic particles. But when you force these two theories to meet, when you take gravity and squeeze it down to quantum scales, something strange happens. They don't play well together. This is where black holes become particularly interesting. Near the event horizon, gravity becomes so intense that it starts affecting the quantum world in ways we're only beginning to understand. That restless quantum activity I mentioned, it becomes important here. Space itself starts to foam, to bubble with particles that pop into existence and vanish again, almost faster than you can imagine. Most of the time, this quantum foam is far too subtle for us to notice. But near a black hole, where spacetime is stretched to its breaking point, these tiny effects start to matter. They accumulate, they build up, they begin to whisper secrets about the nature of reality itself. One of the most beautiful consequences of these quantum whispers is something called Hawking radiation. Stephen Hawking discovered that black holes aren't perfectly black after all. They actually glow, ever so faintly, with a ghostly radiation that emerges from quantum effects near the event horizon. Here's how this ghostly process works. In the quantum world, pairs of particles are constantly appearing out of nowhere. A particle and its opposite, its antiparticle. Normally, they meet each other almost instantly and annihilate, returning to the nothingness they came from. But near the event horizon, something remarkable can happen. The immense gravity can separate these particle pairs. One falls into the black hole while the other escapes into space. From a distance, it looks like the black hole is emitting radiation, as if it's slowly leaking energy back into the universe. This is profound because it suggests that even the most extreme objects in the cosmos, these gravitational prisons from which nothing should escape, are actually giving something back. This radiation carries a deeper message though. It tells us that black holes might not be eternal, after all. Over timescales so vast, they make the lifetime of stars seem like brief flickers. A black hole could actually evaporate completely. It would slowly bleed away its energy through this faint radiation until nothing remains. We'll never witness this process with our own eyes. For the black holes we know about, the ones with masses comparable to stars, the evaporation time is longer than the current age of the universe by factors we can barely comprehend. But the principle matters. It shows us that even at the edge of the most extreme gravitational wells in the cosmos, quantum mechanics still has something to say. These quantum murmurs, reveal something even more profound, though. They expose a fundamental conflict between our two best theories of reality. Relativity describes spacetime as smooth, predictable, geometric. Quantum physics insists that everything is uncertain, probabilistic, fundamentally chaotic at the smallest scales. Near the event horizon, these two worldviews are forced to coexist. Relativity tells us that the event horizon is a clean boundary, a point of no return, where information disappears forever. Quantum mechanics, however, has a strict rule: information can never be truly destroyed. Every bit of data about the universe, every piece of its history, must be preserved somewhere, somehow. This creates one of the most puzzling problems in modern physics. If you burn a book, quantum mechanics says that all the information in that book still exists, just scrambled among the atoms of ash and smoke. Given enough time and impossible precision, you could theoretically reconstruct every word. But what happens if you throw that same book into a black hole? Where does the information go? Classical relativity says it's gone forever, erased from the universe. Quantum mechanics says that's impossible. And so we have a paradox, a fundamental disagreement between our deepest theories about the nature of reality itself. Some scientists think the answer lies in the structure of the event horizon itself. Maybe information doesn't fall into the black hole at all. Maybe it gets smeared across the surface of the event horizon, like a thin holographic film, encoded in ways we don't yet understand. Others believe that entirely new physics must exist, rules we haven't discovered yet, that step in to resolve this cosmic puzzle. Perhaps space-time itself has a deeper structure, hidden layers that become important only under the most extreme conditions. What fascinates me about this is how it connects the largest objects in the universe to the smallest possible scales. A black hole, something so massive it can contain millions of stars, may be fundamentally governed by quantum effects that operate on distances smaller than the nucleus of an atom. These quantum whispers challenge everything we think we know about the universe. They suggest that black holes aren't just cosmic vacuum cleaners that swallow everything and hide it away forever. They might be something far more complex, cosmic computers perhaps, storing and processing information in ways that stretch our imagination. The edge of a black hole becomes a laboratory, where the universe tests its own rules, where gravity and quantum mechanics engage in a conversation we're only beginning to overhear. In those tiny fluctuations, those barely detectable quantum tremors, might lie the keys to understanding not just black holes, but the fundamental structure of reality itself. It's humbling, really. Here we are, trying to understand the universe, and we find that some of our most important clues come from places we can never visit, from effects we can barely detect, from whispers so quiet they're almost lost in the cosmic background. The universe seems to delight in hiding its deepest truths in the most inaccessible places. At the edge of black holes, where space and time bend beyond recognition, where matter disappears and energy transforms, where the very concept of information hangs in the balance, quantum mechanics continues its restless dance. Those quantum murmurs at the edge, soft and nearly imperceptible, may hold the power to revolutionize our understanding of everything. They remind us that even in the most extreme environments the universe can create, the smallest scales of reality still matter, still have their say, still whisper their secrets to anyone patient enough to listen. The boundary between the familiar and the unknown presents us with something profound. Where our current understanding meets its limits, we discover not emptiness, but possibility. The faintest quantum effects near black holes aren't merely academic puzzles, they're glimpses into tomorrow's science. These delicate phenomena might eventually bridge the gap between gravity and quantum mechanics, creating one unified picture of reality. Right now, though, these effects remain elusive. They dance just outside our complete comprehension. Even where gravity dominates everything, the tiniest forces continue their work. They're quietly shaping the next part of our cosmic narrative. These subtle quantum fluctuations at a black hole's edge aren't random disturbances. They're more like gentle melodies, a soft rhythm that plays exactly where our knowledge ends and mystery begins. In everyday life, we think we understand information pretty well. Words on a page stay put. Messages we write seem permanent until we decide to throw them away. When we destroy something, crumple paper or delete files, that information appears gone forever. But deep down in the universe's foundation, information behaves very differently. It's remarkably persistent. Quantum mechanics tells us something startling about information. The fundamental patterns that describe everything in existence, they can never truly disappear. Information might transform completely. It could become unrecognizable, scrambled beyond any hope of easy recovery, but genuine erasure, that's apparently impossible. This creates a fascinating puzzle when we consider black holes. Black holes operate like cosmic one-way streets. Matter crosses their event horizons, pulled by gravity so intense that light itself cannot return. From our perspective outside, whatever goes in simply vanishes. For decades, scientists assumed this was straightforward. Black holes consume everything without regard for quantum rules about information preservation. Then, the contradiction became clear. If black holes genuinely destroy information, they violate fundamental physics principles. The universe doesn't tolerate such contradictions easily. In the 1970s, Stephen Hawking illuminated this paradox through his calculations. He showed that black holes emit radiation, now called Hawking radiation. This emission causes black holes to slowly evaporate over incredibly long timescales. But there's a problem with this radiation. It appears completely thermal, carrying no traces of whatever originally fell into the black hole. If a black hole eventually evaporates entirely, all the information it contained seems lost forever. This conclusion disturbed the physics community because it suggested something impossible. The universe would permanently lose information, yet quantum mechanics remains adamant. Information cannot be erased, not by time, destruction, or even black holes. This launched one of the most intense, ongoing debates in modern science. Many physicists now suspect that information isn't actually lost in black holes. Instead, it might be preserved through subtle, hidden mechanisms. The information could be encoded within spacetime's very fabric. Some researchers propose that information gets smeared across the event horizon. It becomes imprinted there, like invisible writing on an unseen surface. This concept, known as the holographic principle, suggests something remarkable. A black hole might function like a cosmic storage system. Its event horizon acts as a two-dimensional surface that somehow contains complete details of everything that ever fell inside. This might sound bizarre, but it rests on solid, theoretical foundations. The holographic principle implies that our entire three-dimensional universe might actually be encoded on some distant two-dimensional boundary. Black holes wouldn't be exceptions to this rule. They'd be proof of it. They represent the most extreme examples of how the universe preserves information, regardless of how strange or inaccessible that preservation becomes. Other theories venture even further. Some physicists suggest information doesn't remain stuck on the event horizon. Instead, it gets released through subtle pathways, carried away by Hawking radiation. Not a simple thermal energy, but bearing faint quantum-level impressions of whatever once fell in. If this proves correct, black holes aren't information destroyers at all. They're information scramblers. They take everything that falls inside, matter, energy, and information alike, then transform it into something almost unrecognizable. They slowly leak this transformed information back into the universe. It emerges, scattered and encoded in ways we haven't yet learned to interpret. Despite these elegant theories, we still lack a definitive answer. This is the heart of the black hole information paradox. We know information must go somewhere, but we don't understand how or where it's stored. It's as though the universe speaks a language we don't fully comprehend. A language where nothing gets truly forgotten, but everything can be rewritten in forms so alien that they appear completely gone. Consider this analogy. Imagine writing a letter, then shredding it into billions of microscopic pieces. To you, the information seems destroyed. But in principle, every fragment still exists. Someone with infinite patience and precision could theoretically gather those pieces and reconstruct the original message. Black holes might operate similarly. They shred information until it's thoroughly scrambled and unrecognizable, but never truly destroy it. In this strange, almost poetic way, black holes become something beyond cosmic monsters. They transform into libraries, silent, impenetrable libraries, where every book has been torn apart and scattered, every word broken down to its smallest components, yet nothing ever truly lost. If this perspective holds true, it reveals something profound about the universe's nature. It suggests reality is far more orderly than appearances indicate. Beneath the chaos, beneath black holes crushing gravity, there exists a hidden accounting system. The universe maintains records of every particle, every quantum state, every fragment of information that has ever existed. We simply haven't learned how to read these records yet. For now, we can only listen to whispers from theory and mathematics, to hints left by quantum mechanics and relativity, to faint suggestions that the universe possesses a memory far deeper and stranger than our own. Perhaps black holes serve as keepers of that memory. Dark, silent archives positioned at existence's edge. They guard information that refuses to vanish completely. In a universe where everything seems fragile and temporary, there might be no such thing as true loss. Even in a black hole's heart, even at the singularity itself, the story of what once existed may persist, hidden in forms we don't yet understand, waiting for the day when we finally learn to read them. These concepts invite us to reconsider our relationship with permanence and loss. What we perceive as endings might simply be transformations beyond our current ability to recognize. The universe appears to maintain its own vast library, one where checkout is permanent, but nothing is ever discarded. It's all still there, somewhere, somehow, written in a script we're only beginning to glimpse. Black holes have always forced us to confront the limits of what we think we know about reality. For decades, physicists believed that crossing into a black hole would be, surprisingly, rather ordinary. You drift past that invisible point of no return, the event horizon, without feeling anything dramatic. No sudden jolt, no blinding flash, just the smooth continuation of your journey into the unknown. This peaceful picture comes from Einstein's general relativity, which treats space and time as a flowing fabric that bends and curves. According to this view, the event horizon isn't really a physical barrier at all. It's more like an invisible line in space, marking the boundary where escape becomes impossible. Cross it, and you'd continue falling toward the center, unaware that your fate was sealed. But then quantum mechanics entered the conversation, and everything became far more complicated. Quantum physics operates by different rules that sometimes seem to contradict what relativity tells us. One of these rules says that information, the fundamental bits that describe everything in the universe, can never truly be destroyed. This creates a puzzle that has kept physicists awake at night for decades. When Stephen Hawking showed that black holes slowly evaporate by radiating energy, he accidentally created one of the deepest mysteries in modern science. If a black hole eventually disappears completely, radiating away all its mass as heat, what happens to all the information that fell into it? The books, the people, the planets, everything that ever crossed the event horizon. Where does all that information go? Quantum mechanics insists it cannot simply vanish. Information must be preserved somehow. But if the black hole evaporates completely, and if that information somehow escapes in the radiation, then we face an impossible situation. The information would need to exist in two places at once, inside the black hole and in the radiation streaming away from it. This is where the firewall idea emerges, like a desperate solution to an impossible problem. Some physicists propose that nature might resolve this paradox in the most violent way imaginable. Instead of allowing information to be duplicated, the universe might destroy anything that tries to cross the event horizon. The boundary itself might become a wall of pure, destructive energy. Imagine approaching what looks like empty space around a black hole. Everything appears calm, normal. But the moment you touch that invisible boundary, you encounter something unimaginably violent. Not a wall you can see or touch, but a barrier made of quantum energy so intense it would instantly obliterate anything that makes contact. Your atoms wouldn't just be torn apart, they'd be reduced to quantum nothingness. This firewall wouldn't be made of flames or plasma, like we might imagine. It would be something far stranger, a manifestation of quantum mechanics itself, enforcing the laws of physics through pure destruction. The very fabric of space and time would become hostile, turning the event horizon into nature's ultimate boundary. The implications are staggering. If firewalls exist, then black holes aren't the cosmic vacuum cleaners we once thought. They'd be more like quantum furnaces, burning away anything that approaches too closely. The romantic notion of falling into a black hole and experiencing the universe from a completely different perspective would be replaced by instant annihilation. But this creates its own problems. Einstein's relativity has been tested countless times and has never failed. It predicts that space and time should remain smooth and continuous, even at the event horizon. The firewall idea essentially says that relativity breaks down at this crucial boundary, that the smooth fabric of space-time suddenly becomes jagged and violent. Some physicists have proposed even stranger alternatives. What if reality itself depends on your perspective? What if reality itself depends on your perspective? From the outside, watching someone fall toward a black hole, you might see them encounter the firewall and get destroyed at the horizon. But from the perspective of the person falling, they might experience a smooth crossing, unaware of any violence. Two different realities, both equally true, existing simultaneously. This concept, called complementarity, pushes our understanding of reality to its breaking point. It suggests that the universe might not have one single, objective truth about what happens at black hole boundaries. Instead, the truth might be layered, dependent on who's observing and from where. Another possibility involves the holographic principle, one of the most mind-bending ideas in modern physics. This suggests that everything inside a black hole might actually be encoded as information on its surface, like a cosmic hologram. If this is true, then nothing really falls into the black hole at all. Everything that appears to cross the horizon might actually remain encoded on the boundary itself. In this holographic view, the event horizon becomes something like a cosmic hard drive, storing all the information that has ever approached the black hole. There's no need for a violent firewall, because nothing actually needs to be destroyed. The information is preserved right there on the surface, invisible to us but never truly lost. These ideas force us to question fundamental assumptions about space, time, and reality itself. Are space and time truly smooth and continuous as Einstein believed, or are they made up of discrete quantum bits that can behave in unexpected ways? Is information the most fundamental aspect of reality, more basic than matter and energy? The firewall debate touches on something profound about the nature of existence. It asks whether the universe is fundamentally gentle or violent, whether the laws of physics are enforced through harmony or through destruction. At the most extreme boundaries of reality, where space and time themselves begin to break down, which face does the universe show us? What makes this mystery so compelling is that we may never be able to solve it directly. No telescope can peer inside a black hole to see what really happens. No experiment on Earth can recreate the extreme conditions near an event horizon. We're left to follow the mathematics wherever it leads, even when it takes us to places that seem impossible. The search for answers has led physicists to develop new theories that try to unify quantum mechanics and gravity. String theory, loop quantum gravity, and other approaches all attempt to resolve these paradoxes by proposing deeper layers of reality. Perhaps the truth about firewalls lies hidden in these more fundamental theories. But until we have that deeper understanding, we're left with profound uncertainty. The event horizon might be a gentle boundary that allows peaceful passage into the unknown. It might be a wall of quantum fire that destroys anything that approaches, Or it might be something even stranger, something that our current theories can't even imagine. This uncertainty isn't just academic. It reflects our position as conscious beings trying to understand a universe that often seems stranger than fiction. We've built remarkably successful theories that can predict the behavior of everything from atoms to galaxies. But at the edges of our knowledge, where the most extreme conditions exist, we still find ourselves confronting mysteries that challenge our deepest assumptions about reality. The firewall paradox reminds us that science isn't just about finding answers, it's about learning to ask better questions. Each attempt to resolve the paradox has led to new insights about the nature of information, space, time, and consciousness itself. Even if we never definitively prove whether firewalls exist, the journey toward understanding has already expanded our conception of what's possible. Perhaps that's the most profound aspect of this mystery. It exists at the intersection of everything we think we know about physics, forcing different theories to confront each other in ways that reveal hidden assumptions and limitations. The firewall isn't just a barrier that might exist around black holes, it's a barrier in our understanding that we're still trying to overcome. When physicists encounter something that doesn't make sense, they don't just shrug and move on. These contradictions, these puzzles that keep scientists awake at night, they're actually gifts in disguise. They're pointing us toward the places where our understanding breaks down, where new discoveries are waiting to be made. There's this fundamental rule in quantum mechanics that's never been broken, not once. Information cannot be destroyed. It's like the universe's most sacred law. You can scramble information, you can hide it, you can transform it beyond recognition, but you absolutely cannot make it disappear. Think of it like burning a book. The words might turn to ash, but every single detail about those pages, every quantum property of every atom, that information has to go somewhere. Maybe it's in the smoke, maybe it's in the heat, but it's still there, somewhere. Now here's where things get really strange. Black holes seem to violate this rule completely. They swallow everything that gets too close: matter, light, entire stars. Once something crosses that invisible boundary called the event horizon, it's gone forever. At least, that's what we used to think. Stephen Hawking discovered something remarkable about these cosmic monsters. They're not completely black after all. They actually emit radiation, incredibly slowly, over timeframes that make the age of our universe look like a blink of an eye. But here's the problem. This radiation appears to be completely random. It carries no information about what fell into the black hole. So when the black hole finally evaporates completely, all that information seems to have vanished into nothing. This creates what scientists call the information paradox. Either quantum mechanics is wrong, which would shatter one of our most successful theories, or our understanding of black holes is incomplete. Both possibilities are deeply unsettling for physicists who've spent their careers building these theoretical frameworks. Some scientists have proposed truly mind-bending solutions. There's this idea called the holographic principle. Imagine you're looking at a hologram on a credit card. The image appears three-dimensional, but all the information is actually stored on a flat, two-dimensional surface. According to this theory, everything that falls into a black hole isn't really destroyed. Instead, all that information gets encoded on the event horizon itself, like cosmic data storage on the black hole's surface. The really wild part is that some physicists think our entire universe might work this way. Everything we experience, our three-dimensional reality, might actually be a projection from information stored on some distant two-dimensional boundary. It's like we're living inside a hologram without realizing it. String theory offers another fascinating possibility. Instead of thinking about matter as tiny solid particles, string theorists imagine everything is made of incredibly small, vibrating strings. These strings can vibrate in different patterns, creating all the particles and forces we observe. In this framework, black holes don't destroy information, they just scramble it so thoroughly that it becomes unrecognizable. The information is still there, but it's encoded in ways we can't decode yet. Then there are the truly radical ideas. Some physicists suggest that nothing actually makes it past the event horizon alive. Instead of gently falling into the black hole, Anything that gets close enough encounters a wall of devastating energy that destroys it instantly. It sounds violent, but it would solve the information problem. If nothing survives to fall in, then no information gets lost inside. But maybe we're thinking about this all wrong. Maybe the real issue is that we don't have the right tools yet. We understand gravity pretty well on large scales, thanks to Einstein's relativity. We understand quantum mechanics pretty well on small scales, but black holes exist right at the boundary where these two theories meet, and they don't play nicely together. There might be a deeper theory out there, something that unifies quantum mechanics and gravity in ways we haven't imagined yet. In this hypothetical framework, the information paradox might simply dissolve. Not because we solved it, but because we finally learned to ask the right questions. Throughout history, these kinds of paradoxes have been revolutionary. When scientists couldn't explain why hot objects glow the way they do, that puzzle led to quantum mechanics. When Mercury's orbit didn't quite match Newton's predictions, that discrepancy helped Einstein develop relativity. The problems that seem impossible to solve often become doorways to entirely new ways of understanding reality. The black hole information paradox forces us to think about some of the deepest questions imaginable. What is information, really? Is it a fundamental part of reality, like matter and energy? What does it mean for something to exist if we can never observe it? These aren't just technical problems for physicists to solve. They're questions about the nature of existence itself. Consider how strange it is that we can even ask these questions. Here we are, collections of atoms that somehow became conscious, trying to understand the most extreme objects in the universe. We're using mathematics and experiments to probe regions of space-time so warped that our everyday intuition completely fails us. The fact that this paradox exists, that it continues to puzzle the brightest minds in physics, is actually kind of beautiful. It means we haven't figured everything out yet. There are still mysteries out there, still discoveries waiting to be made. In a universe that often seems predictable and mechanical, these unsolved puzzles remind us that reality is far stranger and more wonderful than we imagined. Every time physicists gather to discuss this problem, every paper written about it, every late-night conversation between colleagues, we edge a little closer to understanding. Maybe the solution is already out there, hidden in some equation that hasn't been written yet, or waiting in some experiment that hasn't been performed. The paradox sits there like a locked door, challenging us to find the right key, and maybe that's exactly as it should be. Maybe the universe is supposed to be mysterious, supposed to keep us guessing and wondering and reaching for answers just beyond our grasp. The questions that frustrate us the most might also be the ones that define us as a species, the ones that keep us looking up at the night sky and asking what secrets are hidden in the darkness between the stars. Space appears perfectly empty, but this is one of nature's greatest illusions. Even in the darkest regions between stars, quantum fields bubble with constant activity. Particles pop into existence from nothing, live for impossibly brief moments, then vanish back into the void. This dance happens everywhere, all the time, completely invisible to us. The universe maintains a kind of restless energy, even in its most barren corners. When Stephen Hawking examined these quantum fluctuations near black holes in the 1970s, he discovered something extraordinary. The immense gravitational field of a black hole can tear apart these paired particles before they destroy each other. One particle gets dragged across the event horizon, trapped forever. The other escapes into space, carrying away a tiny amount of energy. To someone watching from a safe distance, it looks like the black hole is glowing very faintly. This radiation emerges so slowly that it defies human comprehension. A black hole with the mass of our sun would take longer than the age of the universe to lose even a fraction of its bulk through this process. Yet the principle transforms everything we thought we knew about these cosmic monsters. They're not eternal after all. They leak energy, bit by bit, shrinking over unimaginable spans of time. The mathematics behind Hawking radiation reveals something unsettling. As a black hole evaporates, it appears to be radiating completely random heat. There's no trace of the stars, planets, or spacecraft that fell in over billions of years. All that information seems to vanish completely. This creates a fundamental problem, because quantum mechanics insists that information cannot be destroyed, only transformed or hidden. Picture a book falling into a black hole. According to classical physics, that book is gone forever. But quantum theory demands that every detail about that book, every word, every molecule, must be preserved somewhere in the universe. If Hawking radiation carries no information, then physics has a serious contradiction on its hands. Many scientists now believe the radiation must encode information in ways we don't yet understand, perhaps through subtle quantum correlations that span enormous distances. The idea that black holes might actually preserve information changes how we think about the nature of reality itself. Some physicists propose that the event horizon isn't really a surface at all, but a kind of holographic projection. Others suggest that space and time emerge from more fundamental quantum processes, like pixels making up a vast cosmic screen. These theories push us toward a universe that's stranger and more interconnected than we ever imagined. Consider what happens to black holes in the far future. Long after every star burns out, after galaxies drift apart and cool, black holes will be among the last objects remaining. They'll continue their slow evaporation in a universe grown cold and dark. Smaller black holes actually radiate faster than large ones, so as they shrink, they brighten. In their final moments, they'll release a brilliant flash of energy before disappearing completely. This process operates on timescales that make geological ages seem like heartbeats. The smallest black holes we might create in laboratories would evaporate almost instantly. Stellar mass black holes take longer than 10 to the 67th years to fade away. The supermassive giants at the centers of galaxies will persist for 10 to the 100 years or more. These numbers stretch beyond intuition, beyond meaning, yet they represent real processes happening right now. The temperature of Hawking radiation depends inversely on the black hole's mass. Paradoxically, the larger the black hole, the colder its radiation. A solar mass black hole radiates at just 60 billionths of a degree above absolute zero. That's far colder than the cosmic microwave background radiation that fills space. This means most black holes are actually absorbing more energy from their surroundings than they emit. They'll continue growing until the universe expands and cools further. Only in a much older, colder cosmos will Hawking radiation begin to dominate. Then, black holes will truly start shrinking, entering their long twilight of evaporation. It's a process that connects the quantum world of subatomic particles with the grandest structures in the universe. The same principles that govern atoms and molecules also determine the fate of objects millions of times more massive than our Sun. Scientists continue debating whether we'll ever detect Hawking radiation directly. The effect is so weak that it's completely swamped by other sources of energy. Even in the perfect vacuum of space, black holes absorb stray photons and particles faster than they evaporate. Detecting this radiation would require isolating a black hole in conditions far more sterile than anything we can create. Some researchers have proposed laboratory analogues using sound waves in flowing fluids or light pulses in special materials. These experiments might reveal similar physics on much smaller scales. If successful, they could provide insights into how quantum mechanics and gravity interact in extreme conditions. The universe might be teaching us its deepest secrets through phenomena we can recreate on a tabletop. The philosophical implications ripple outward, like waves from a disturbed pond. If black holes preserve information, then the universe remembers everything that ever happened. Every thought, every moment, every fleeting experience becomes part of an eternal record encoded in the fabric of space-time itself. Nothing is truly lost, only transformed into patterns too complex for us to read. This connects to ancient questions about permanence and change. Even the most powerful, destructive forces in nature are subject to time's slow erosion. Black holes, which can tear apart stars and devour entire solar systems, ultimately succumb to quantum processes operating at the smallest possible scales. The universe contains its own mechanisms for recycling even the most concentrated forms of matter and energy. Perhaps there's something profound in this cosmic bookkeeping. The same universe that creates black holes also ensures their eventual dissolution. Matter and energy flow through cycles we're only beginning to understand, preserved and transformed across scales of space and time that dwarf human experience. We exist within a vast, patient system that appears to forget nothing, even as it constantly reinvents itself. Hawking radiation represents one of the most elegant intersections of physics and philosophy. It emerges from the marriage of quantum uncertainty and gravitational certainty, producing effects that unfold over cosmic ages. In studying these phenomena, we glimpse the universe's deepest organizing principles, the rules that govern everything from the smallest fluctuations to the largest structures. The radiation whispers secrets about the nature of information, energy, and time itself. These whispers are far too faint for us to hear directly, but mathematics allows us to eavesdrop on conversations between quantum mechanics and general relativity. In doing so, we discover that even the darkest objects in the universe are not truly dark, that even the most permanent features of reality are slowly, imperceptibly changing. Black holes exist in a realm of time that stretches beyond anything our minds can truly grasp. These cosmic giants don't follow the same rules as everything else in the universe. While stars burn bright and die, while galaxies slowly drift apart and fade, black holes simply wait. They sit there patient beyond measure, holding their ground in space for periods so long that numbers start to lose all meaning. The universe around us is roughly 14 billion years old. That already feels impossible to imagine, but it's nothing compared to how long a black hole will survive. A typical black hole, the kind that forms when a massive star collapses, will take around 10 to the 67th power years to completely disappear. That's a 1 with 67 zeros after it. To put that in perspective, every star that has ever existed, every galaxy that has ever shined, will be long gone before that black hole even begins to look tired. And the really massive ones, the supermassive black holes sitting at the centers of galaxies like our own Milky Way, they live even longer. Their lifespans are measured in numbers so large, we have to write them as mathematical expressions because there isn't enough space in the universe to write out all those zeros. This incredible longevity comes from something called Hawking radiation. It's one of the strangest discoveries in physics, and it tells us that black holes aren't actually perfectly black. They give off radiation, but so slowly, so faintly, that it's almost like watching paint dry on a cosmic scale. Each tiny particle that escapes takes a microscopic amount of mass with it. The black hole shrinks, but by such an impossibly small amount that you'd need to wait geological ages just to measure the difference. There's something almost philosophical about this process. Here are objects so powerful they can bend space and time itself, yet they're slowly, quietly dissolving away. It's like the universe has built in its own recycling system, but one that operates on a schedule that makes glaciers look speedy. As we look toward the far future, long after our sun has died, long after every star in the night sky has burned out, black holes will still be there. They'll be the last major players in a universe that has grown dark and cold. The great stellar nurseries will be empty, the spiral arms of galaxies will have dispersed, and space will be filled mostly with the cooling remnants of dead stars. White dwarfs slowly fading to black, neutron stars spinning down to stillness, lonely planets drifting through the void without any sun to warm them. In that distant epoch, black holes will be like the last campfires at the end of a very long party. They'll dominate through sheer persistence, the final massive objects with enough gravitational pull to still shape their surroundings. But even then, that invisible Hawking radiation will keep doing its work, particle by particle, bit by bit. These cosmic monuments will continue their incredibly slow surrender to entropy. The mathematics behind this process reveals something beautiful and strange. As a black hole loses mass, its temperature actually increases. It's counterintuitive, like a dying ember that somehow grows hotter as it shrinks. For most of its incredibly long life, this heating effect is negligible. The radiation remains a whisper, barely distinguishable from the background hum of empty space. But as the black hole approaches its final moments, something dramatic happens. The shrinking accelerates. What was once an imperceptible trickle becomes a stream, then a torrent. The black hole's event horizon, that invisible boundary where escape becomes impossible, starts collapsing faster and faster. And then, after eons of patient dissolution, the end comes suddenly. The last black hole in the universe will die not with a whimper, but with a brilliant flash of energy, like a cosmic firework celebrating the conclusion of the longest show ever performed. But for the vast majority of its existence, perhaps 99.999% of its lifetime, the black hole will be engaged in this quiet, invisible process of evaporation. It's a kind of cosmic meditation, a slow-motion ballet performed on a stage so vast that entire civilizations could rise and fall between movements. This vision of the far future forces us to confront some uncomfortable truths about the nature of existence. In that distant time, when the last black holes are finally evaporating away, the universe will be approaching what physicists call heat death. Not a fiery apocalypse, but rather a state of maximum entropy, where all energy has been evenly distributed and no more useful work can be done. It's a future where temperature differences have disappeared, where all the fuel for stars and life and change has been exhausted. The universe becomes like a cup of coffee that's been sitting out for eternity, finally reaching room temperature and staying there forever. No more hot spots, no more cold spots, just uniform, lukewarm existence, stretching on without end. Yet there's something oddly comforting about this vision. The universe doesn't end in violence or chaos. It ends in perfect balance, perfect stillness. Every debt paid, every account settled. The initial burst of energy from the Big Bang spread out across space and time until it finally comes to rest. When we think about our own lives against this backdrop, something interesting happens. Our daily concerns, our urgent deadlines, our worries about the future, they all exist in this tiny slice of cosmic time when the universe is still young and energetic. We live in an era of stellar birth and galactic collision, of planets forming and life evolving. In cosmic terms, we're living during the universe's childhood, when everything is still happening quickly and dramatically. Black holes remind us that the cosmos operates on multiple timescales simultaneously. While we experience seconds and minutes and years, black holes are engaged with deep time, with spans so long that the difference between 1,000,000 years and 1,000,000,000 years becomes meaningless. They're like cosmic librarians, keeping careful records of everything that falls into them, holding on to information for periods that dwarf the lifetime of any civilization that might want to read those records. There's also something profound about the way black holes connect the very small with the very large. Hawking radiation emerges from quantum effects, right at the edge of the event horizon, where the strange rules of quantum mechanics meet the extreme curvature of spacetime. The fate of these cosmic giants depends on the behavior of virtual particles, tiny fluctuations in the quantum vacuum that most of us will never see or directly experience. This connection between the microscopic and the astronomical runs throughout modern physics. The same quantum processes that determine how atoms behave also control how black holes evaporate. The same fundamental constants that govern chemistry also determine whether the universe will expand forever or eventually collapse. We live in a cosmos where the very small and the very large are intimately connected, where the behavior of subatomic particles can determine the fate of objects millions of times more massive than our Sun. As the last black holes in our universe slowly evaporate away, they'll be releasing information back into the cosmos. Everything that ever fell into them, every star and planet and spacecraft, every bit of data about the universe's history, will finally escape in encoded form within that Hawking radiation. It's as if the universe has a built-in backup system, ensuring that nothing is ever truly lost, just transformed and scattered and mixed up beyond recognition. In those final moments, when the last black hole finally disappears, the universe will have completed a kind of circle. What began with tremendous concentration of energy and matter will end with perfect diffusion, everything spread as evenly as possible across infinite space. The cosmos will have finished the longest possible game of solitaire, finally managing to arrange all the cards in perfect order. Across the universe, gravity creates some of the most puzzling objects we know. Black holes stand as cosmic mysteries, swallowing light itself, yet slowly revealing secrets that challenge everything we thought we understood about reality. These gravitational monsters aren't quite what they seem. While they devour stars and planets with unstoppable force, they also participate in one of nature's most delicate processes. Deep within the quantum realm, something remarkable happens at their edges. Particles appear from seemingly empty space, dancing at the boundary between existence and oblivion. This quantum dance creates what scientists call Hawking radiation. Named after the physicist who predicted it, this process turns black holes from perfect consumers into gradual givers. The radiation emerges so faintly that detecting it remains nearly impossible with current technology, yet this whisper of energy carries profound implications for cosmic fate. Consider the strange mathematics of black hole temperature. Unlike a campfire or star, black holes grow hotter as they shrink. This backwards behavior defies our everyday experience. A massive black hole sits colder than the space around it, barely warmer than absolute zero. But as it loses mass through radiation, its temperature climbs steadily upward. The timescales involved stretch imagination beyond breaking points. A black hole with our sun's mass would take longer to evaporate than the current age of the universe multiplied by countless trillions. During most of this time, the radiation emerges so slowly that the black hole appears perfectly stable, unchanging across billions of years. Yet change does come, eventually. As the black hole shrinks, the radiation intensifies, temperature rises, energy output increases, and the process accelerates like water spiraling down a drain. What began as an imperceptible trickle becomes a torrent, then finally explodes in a brilliant flash that releases the remaining mass as pure energy. This gradual transformation raises questions about the nature of information itself. Everything that falls into a black hole carries information, from the quantum properties of particles to the complex arrangements of atoms in stars and planets. Classical physics suggested this information vanished forever, destroyed beyond recovery, but quantum mechanics tells a different story. The fundamental laws of physics seem to forbid the complete destruction of information. This creates a paradox, a conflict between our understanding of gravity and quantum theory. Some scientists propose that Hawking radiation might carry away the trapped information, encoded in subtle correlations between the escaping particles. The mathematics becomes incredibly complex here, involving concepts that push the boundaries of current knowledge. Yet the basic idea offers hope for cosmic bookkeeping. Instead of permanent erasure, black holes might function as cosmic recyclers, slowly returning their contents to the universe in scrambled but recoverable form. This recycling process connects the smaller scales of reality with the largest. Quantum effects, normally confined to atoms and molecules, reach across space to influence galactic evolution. The energy released by evaporating black holes could seed new star formation billions of years in the future, when most stars have already burned out. Black holes also serve as natural laboratories for testing extreme physics. Their intense gravity warps space and time in ways impossible to recreate on Earth. The radiation they emit provides clues about how quantum mechanics behaves in the presence of strong gravitational fields, bridging two of our most successful but incompatible theories. The event horizon, that invisible boundary around each black hole, marks where our normal understanding breaks down. Time appears to stop for outside observers watching matter fall inward. Yet from the perspective of the falling matter, the journey continues normally until reaching the central singularity, where physics as we know it fails completely. These paradoxes point toward deeper truths about reality structure. Space and time might not be fundamental, but could emerge from more basic quantum processes. Information might exist in forms we haven't yet learned to recognize or measure. The universe might operate according to principles that seem impossible from our limited perspective. As black holes evaporate, they return their energy to an expanding cosmos, growing ever colder and more dilute. This process represents one chapter in the universe's long story of transformation. Stars form from gas clouds, burn through their nuclear fuel, then collapse or explode, sometimes creating the very black holes that will eventually evaporate billions of years later. nothing in the cosmos remains permanent. Even the most stable protons might decay given enough time, dissolving into lighter particles and energy. The universe appears headed toward a state of maximum entropy, where all energy spreads evenly through space, leaving no gradients to drive further change. Yet within this apparent march toward cosmic heat death, complexity emerges and flourishes. Galaxies form, stars ignite, planets coalesce, and perhaps life appears to contemplate its own existence. Black holes, those supposed destroyers of information and complexity, might actually preserve and eventually restore what they consume. This interplay between creation and destruction, order and chaos, permanence and change, reflects patterns visible throughout nature. Mountains rise through tectonic forces, then erode grain by grain. Rivers carve canyons while depositing sediments downstream. Living things grow and reproduce before returning their atoms to the cycle of existence. The fading of black holes reminds us that even the most extreme objects participate in cosmic recycling. Matter and energy change forms but never disappear completely. Information might survive in ways we're only beginning to understand. The universe continues its patient work of transformation, turning yesterday's endings into tomorrow's beginnings. The cosmos holds secrets that challenge everything we think we know about reality. Scientists have discovered something remarkable, something that suggests the entire universe might be far more connected than we ever imagined. When physicists study black holes, they find these incredible objects at their center, singularities where all matter gets crushed into points with infinite density. Space and time break down completely at these spots. The normal laws of physics simply stop working. But here's where things get really interesting. Our universe started from what looks like the exact same kind of singularity. About 13.8 billion years ago, everything that exists today, all the matter, all the energy, even space itself, was compressed into a single point. Then it expanded outward, creating the cosmos we see around us. This wasn't an explosion happening somewhere in empty space. Space itself grew from that tiny point, stretching outward, carrying matter with it as it expanded. Think about that for a moment. Everything around you, every atom in your body, every star in the sky, came from that one incredibly small beginning. Some researchers are starting to wonder if maybe the universe never really stopped being a singularity. Maybe it just unfolded, like origami being opened up, but still fundamentally the same piece of paper. The expansion might have revealed what was always there, rather than creating something entirely new. This raises a profound question about the nature of existence itself. Are we separate beings living inside a universe, or are we actually pieces of the universe experiencing itself? If everything came from the same singular point, then in some sense, we're all connected at the most basic level possible. Quantum physics gives us hints that this connection might be real. Scientists have found that particles can become entangled, meaning they influence each other instantly, no matter how far apart they are. It's as if they remember being part of the same system, even when separated by vast distances across space. Einstein's work on relativity showed us that space and time aren't separate things. They're woven together into a single fabric called space-time. This fabric can bend and stretch. It can even fold in on itself under extreme conditions, like near black holes or during the universe's beginning. The mathematics behind these ideas leads to some wild possibilities. Some theories suggest that black holes might not just destroy things, they might actually create new universes. Picture a cosmic tree, where each black hole sprouts a new branch of reality. Our universe could be growing from the singularity inside a black hole in some other cosmos. If that's true, then singularities are both endings and beginnings. They're points where one reality collapses and another unfolds. Creation and destruction become two faces of the same process, forever cycling through the cosmos. This perspective completely changes how we think about time. From our human viewpoint, time moves forward in a straight line. We experience past, present, and future as separate moments. But if the universe is really one big unfolded singularity, then maybe all of time exists at once, like a vast sculpture that we can only see one slice at a time. Every moment that has ever happened, every moment that will happen, might all be part of this single, eternal structure. The birth of stars, the formation of planets, the emergence of life, even our own thoughts right now, could all be facets of one timeless reality. Black holes scattered throughout space might be windows into this deeper truth. When matter falls into a black hole, it doesn't disappear. According to the laws of physics, information can't be destroyed. It has to go somewhere. Maybe it gets encoded into the structure of space-time itself, becoming part of the universal memory. The singularities at black hole centers might be places where the universe remembers what it really is, points where the illusion of separation breaks down and everything reveals its fundamental unity. These aren't monsters destroying reality, but rather glimpses of reality's true nature. Consider what this means for our place in the cosmic story. We're not just observers watching the universe from the outside. We're expressions of the universe's own consciousness, ways that the cosmos has developed to understand itself. Every thought, every feeling, every moment of awareness is the universe experiencing its own existence. The same forces that forged stars in the hearts of ancient nebulae flow through our bodies right now. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was created in stellar furnaces billions of years ago. We are literally made of star stuff, carrying the cosmos within us. Some theories predict a universe will eventually expand so much that it grows cold and empty, with all the stars burning out and all the black holes evaporating away. Maybe the expansion will reverse, and everything will collapse back into a singularity, only to expand again in an endless cycle. If that's true, then existence itself might be like breathing, expanding and contracting forever, with no ultimate beginning or end. Each cycle could create slightly different conditions, different physical laws, different possibilities for matter and energy to organize themselves. The singularity that started everything might not be gone. It might have just stretched itself across the entire universe, becoming the hidden foundation beneath all of reality. Every galaxy, every planet, every living thing could be a different note in the same cosmic symphony, all playing variations on the original theme. Exit. This view transforms our understanding of connection and separation. The distances between stars, the boundaries between objects, even the distinction between past and future, might all be illusions created by our limited perspective. At the deepest level, everything might be one vast interconnected whole. The universe doesn't just contain singularities. The universe might be a singularity, forever exploring its own infinite possibilities through the dance of matter and energy across space and time. We're not separate from this cosmic exploration. We are it, experiencing itself through billions of different eyes, reaching toward understanding through countless different minds. When we picture the cosmos, most of us imagine a simple timeline. There's a start, there's a middle, and somewhere far ahead, there's an ending. But the more we dig into the science, the stranger things become. The universe might not be the straightforward story we thought it was. Consider what happens at the very extremes of physics. Singularities are these bizarre points where everything we know breaks down completely. Space crumples up, time gets twisted beyond recognition, and all the matter and energy in existence gets squeezed into something impossibly small. We find these weird spots at the hearts of black holes, and we think one of them started our entire universe during the Big Bang. Here's where it gets interesting though. If a singularity kicked off our universe, what's stopping another one from doing the same thing again? And again after that? This brings us to one of the most mind-bending ideas in modern cosmology, the cyclic universe model. Picture this. Instead of our cosmos having a clear beginning and end, it's stuck in this endless loop. It grows bigger and bigger, evolves for billions of years, then eventually collapses back in on itself. But instead of that being the final chapter, all that compressed matter and energy explodes outward once more, creating a brand new universe from scratch. It's almost like the cosmos has learned how to hit its own reset button. Every cycle wipes the slate completely clean, then starts writing a new story on top of the old one. There's something oddly comforting about this idea, isn't there? Even when everything ends, it doesn't really end. It just transforms into something else entirely. But here's the puzzle that keeps scientists up at night. Would each new universe be exactly the same as the one before? Like some cosmic version of a broken record, playing the same tune over and over for eternity? Or would each cycle shuffle the deck differently, creating completely new rules for how physics works, how galaxies form, how life might emerge? Some researchers think each reboot could produce universes so different from ours that we wouldn't even recognize them as universes at all. Different laws of nature, different types of particles, maybe even different numbers of dimensions. It's like nature experimenting with itself, trying out new recipes for reality. Then there are the even wilder theories. Some physicists suggest we might be living in just one branch of an enormous multiverse tree. In this picture, collapsing universes don't just reset themselves. They give birth to multiple offspring, each one branching off to become its own separate reality. While our universe might fade away someday, countless others keep sprouting from this cosmic family tree. Black holes make this whole story even stranger. There are some speculative ideas floating around that suggest every black hole in our sky might be more than just a gravitational monster. Each one could be a doorway, a birth canal for an entirely new universe. Inside that crushing singularity, space and time might pinch themselves off from our reality and create something completely independent. If this turns out to be true, then our entire universe might actually be the interior of a black hole that formed in some other reality. And every black hole we can see through our telescopes, from the small ones created by dying stars to the supermassive giants at the centers of galaxies, all of them could be nurturing their own baby universes right now. Think about that for a moment. Those distant points of darkness scattered across our night sky might each contain entire realities, complete with their own galaxies, their own stars, maybe even their own versions of planets and life forms, beings who look up at their own night sky and wonder about the same mysteries we're pondering right now. This paints a picture of existence that's almost fractal in nature. Universes within universes, each one contained inside the black holes of the one above it, each one creating new black holes that spawn the next generation below. It's like those Russian nesting dolls, but instead of wood and paint, we're talking about the fundamental structure of all reality. The math behind these ideas is incredibly complex, but the basic concept taps into something deeply familiar. We see cycles everywhere in our daily lives. Day follows night, seasons change and repeat. Generations of living things are born, grow old, and pass away to make room for the next wave. Maybe the universe is just doing the same thing, but on a scale so vast that entire cosmic epochs are like single heartbeats in some unimaginably long rhythm. Current observations suggest our universe is actually speeding up its expansion, not slowing down toward a collapse. This points more toward a heat death scenario, where everything gradually spreads out and cools down until no new structures can form. But even in that case, there are theoretical ways a cyclic process could still kick in, given enough time and the right quantum fluctuations. Some versions of string theory and quantum gravity suggest that what we call the Big Bang might not have been the absolute beginning of everything. It could have been more like a bounce, a moment when a previous universe that had collapsed down to its minimum possible size suddenly rebounded outward again. The extreme densities and energies involved make it nearly impossible to see any traces of what came before, but the mathematical frameworks allow for it. There's also the question of what physicists call the arrow of time. In most of these cyclic models, each new universe would have its own fresh arrow of time, its own direction from past to future. This means the cycle itself might exist outside of time as we understand it, in some higher dimensional space where the concepts of before and after work differently than they do for us. These ideas push us to reconsider what we mean when we talk about existence and identity. If the universe really does go through infinite cycles, creating and destroying itself over and over, then everything that ever was, or ever will be, gets erased and rebuilt countless times. Yet in a strange way, the pattern persists. The story continues. Even if the characters and settings get completely rewritten with each telling, it makes you wonder about permanence and meaning in a whole new light. Nothing lasts forever in any individual universe, but the capacity for things to exist, for complexity to emerge, for consciousness to look up at the stars and ask questions. That seems to be woven into the very fabric of whatever process keeps the cosmic cycle turning. Even if we never get definitive proof that cosmic reboots actually happen, the possibility alone changes how we might think about our place in the grand scheme of things. We're not just temporary arrangements of atoms in a universe heading toward emptiness and silence. We might be part of an eternal conversation that reality is having with itself, exploring every possible way that matter and energy and space and time can be arranged and rearranged. Picture space expanding, stretching itself thinner and thinner, until even the concept of distance becomes meaningless. We're talking about a time so far in the future that our current universe would seem like just the opening notes of an incredibly long song. The quantum world keeps humming its faint melodies, even when everything else has gone silent. These tiny fluctuations, smaller than anything we could ever measure, might be whispering secrets about what comes after the end. Scientists call this final destination heat death, but that name doesn't quite capture the strange beauty of it all. It's more like the universe finally exhaling, after holding its breath for trillions upon trillions of years. Every bit of energy finds its place, spreads out evenly, no longer rushing from hot to cold, because there's no difference left between them. The fundamental forces that built galaxies and carved out the structures we know today, they've all finished their work. Gravity spent eons pulling matter together, creating the cosmic architecture of stars and planets and black holes. But even gravity has limits, and when there's nothing left to pull together, it simply waits in the emptiness. The strong nuclear force that holds atoms together, the electromagnetism, they all reach a kind of cosmic retirement. Not because they've weakened, but because there's nothing left for them to act upon. Not because there's nothing left for them to act upon. Black holes, those monsters that devour light itself, they don't last forever, either. Stephen Hawking showed us that they leak energy through radiation, incredibly slowly, but steadily. A black hole the mass of our sun would take longer than the age of the universe multiplied by itself, countless times to finally evaporate. But time, at this scale, has patience beyond our imagination. Every black hole eventually gives up its last bit of energy and fades into the background hum of space. The strangest part might be how quiet it all becomes. We think of space as silent already, but that's only because sound needs matter to travel through. This future silence runs much deeper. It's the silence of a universe where motion itself has lost its purpose. Stars no longer burn because there's no more hydrogen to fuel them. Planets no longer orbit because there are no more stars to orbit around. Even the basic particles of matter drift so far apart that they might as well be alone in their own private universes. Time takes on a completely different meaning when nothing changes anymore. We measure time by watching things move, by counting cycles, by observing cause and effect. But what happens to time when there are no more causes, no more effects, just an endless present moment stretching in all directions? Some physicists argue that time itself might cease to exist in any meaningful way. Others suggest it continues, but becomes more like an infinite, unchanging note than a melody with rhythm and progression. The temperature of this future universe approaches what scientists call absolute zero, but never quite reaches it. Those quantum fluctuations we mentioned earlier, they ensure that even in the deepest cold, there's still a tiny amount of energy stirring in the vacuum. It's as if the universe refuses to completely stop moving, holding on to the faintest whisper of activity, even when everything else has wound down. Galaxies that once danced around each other in cosmic ballets will have drifted so far apart that no signal from one could ever reach another. The expansion of space itself carries them beyond each other's horizons. If somehow, impossibly, there were still observers in this far future, each one would see only darkness in every direction. They would exist in a universe that appears to contain nothing but themselves. But here's where the philosophy gets interesting. Is this really an ending, or is it more like a pause between movements of a symphony? Some theories suggest that quantum fluctuations, given enough time, and we're talking about timescales that make the current age of the universe seem like a split second, could randomly organize themselves into new structures, maybe even new universes bursting forth from the apparent emptiness like flowers blooming in an infinite desert. The mathematics of infinity allows for possibilities that seem impossible. In an infinite amount of time, with quantum fields constantly fluctuating at the smallest scales, every possible arrangement of matter and energy becomes not just possible, but inevitable. This could mean new Big Bangs, new cosmic histories, new stories of stars and planets, and perhaps even new forms of consciousness to contemplate it all. Energy conservation laws still apply, even at the edge of everything. The total amount of energy in the universe remains constant, but it spreads itself so thinly that it becomes nearly impossible to gather together again. It's like trying to collect all the air from a room after it's leaked out into the entire atmosphere of Earth. The energy is still there, but it's lost the concentrated form that makes things happen. Matter itself might not be permanent on these vast timescales. Protons, the building blocks of atomic nuclei, might slowly decay given enough time. This is still theoretical, but if it happens, even the atoms that make up whatever remains in that far future would eventually dissolve into lighter particles and energy. The universe would become not just empty of structure, but empty of the very components that could build structure. What emerges from all this is a picture of cosmic completion rather than cosmic failure. Every possibility that physics allows gets explored. Every star that can form does form. Every black hole that can exist does exist. The universe experiences everything it's capable of experiencing, and then settles into a state of perfect equilibrium. It's not death in any sense we would recognize, but rather a kind of cosmic fulfillment. This ultimate stillness represents something profound about the nature of existence itself. All the complexity we see around us, from the intricate chemistry of life to the vast structures of galaxy clusters, emerges from and returns to simplicity. The arc of the universe bends toward a kind of elegant minimalism that exists beyond time and change. In that final state, the universe doesn't struggle or strive. It simply is, perfectly and completely, in a way that encompasses all the struggling and striving that came before. Time moves differently near the edges of reality. When massive stars collapse into black holes, they create regions where minutes stretch into hours, where the familiar tick of seconds becomes something almost unrecognizable. These cosmic giants don't just bend space, they actually warp the very fabric of time itself. It's a reminder that time isn't as constant as we imagine it to be in our daily lives. The universe operates on scales that make our human experience feel like a single breath. Stars live for millions, sometimes billions of years, burning through their nuclear fuel with a patience we can barely comprehend. When they finally exhaust their energy, the largest ones don't simply fade away, they collapse inward with such force that they create tears in space-time itself. Black holes represent something profound about the nature of existence. They're not really holes at all, but regions where gravity has become so intense that nothing, not even light, can escape once it crosses a certain boundary. This boundary, called the event horizon, marks a point of no return that exists nowhere else in our experience. What happens inside a black hole remains one of the great mysteries of physics. Matter gets compressed into what scientists call a singularity, a point where the normal rules of physics break down completely. It's a place where our understanding reaches its limits, where mathematics itself seems to give up trying to describe reality. The concept of infinity appears again and again in cosmology. The universe might be infinite in size, stretching endlessly in all directions, or it might curve back on itself, creating a closed loop that has no true edge. Either way, we're dealing with something that challenges our everyday understanding of space and boundaries. Gravity shapes everything we see on the largest scales. It pulls galaxies together into vast clusters, creates the spiraling arms of stellar neighborhoods, and governs the dance between planets and their stars. This fundamental force operates across distances so vast that light, The fastest thing in the universe takes billions of years to traverse them. The story of cosmic evolution unfolds like chapters in an incredibly long book. First came the initial expansion, when space itself stretched and cooled from unimaginable heat. Then the first atoms formed, followed by the first stars, the first galaxies, and eventually the complex structures we observe today. Energy flows through the cosmos in patterns that follow predictable laws. Hot regions cool down, cold regions absorb heat, and gradually everything moves toward a state of equilibrium. This process happens in stars, in planets, and across the entire observable universe. It's like watching a cosmic tide that always flows in one direction. The concept of heat death describes a future state where all energy has been distributed evenly throughout space. No more stars would form, no more nuclear fusion would occur, and the universe would reach a kind of maximum entropy. It sounds ominous, but it would happen so slowly that entire civilizations could rise and fall countless times before any noticeable change occurred. Quantum mechanics suggests that even empty space isn't truly empty. Virtual particles constantly pop into existence and disappear again, creating what physicists call quantum foam. This activity at the smallest scales might hold clues about how new universes could emerge from apparent nothingness. The idea of cyclical universes has appeared in many cultures throughout history. Modern physics explores whether our cosmos might indeed go through cycles of expansion and contraction, death and rebirth. If true, what we call the beginning might just be the latest in an infinite series of cosmic renewals. Information theory has become crucial to understanding black holes and the universe itself. Some physicists argue that information can never be truly destroyed, only transformed or hidden. This principle suggests that everything that has ever existed leaves some kind of permanent mark on reality. The observable universe has an edge, but not because space ends there. Instead, we see a boundary created by time itself. Light from the most distant regions has been traveling toward us since shortly after the cosmic beginning, carrying information about the universe's earliest moments. Dark energy remains one of the biggest puzzles in cosmology. This mysterious force appears to be accelerating the expansion of space, pushing galaxies apart at an ever-increasing rate. About 70% of the universe consists of this invisible, poorly understood component. Temperature plays a fundamental role in cosmic evolution. The universe began incredibly hot and has been cooling ever since. This cooling allowed the first particles to form, then atoms, then stars, creating the temperature differences that drive all the processes we observe today. The mathematics of infinity creates paradoxes that challenge our intuition. Some infinities are larger than others, a concept that seems impossible but follows logically from mathematical principles. These ideas become relevant when discussing the ultimate fate of space and time. Consciousness itself might be connected to these cosmic processes in ways we're only beginning to understand. The atoms in our bodies were forged in stellar cores, making us quite literally made of star stuff. Our ability to contemplate the universe represents matter becoming aware of itself. The gentle drift toward cosmic equilibrium happens so gradually that it's almost imperceptible, even on astronomical timescales. Galaxies slowly move apart, stars gradually burn out, and black holes eventually evaporate through a process called Hawking radiation. It's change measured in eons rather than years. Human perspective on these cosmic timescales reveals something beautiful about our place in the universe. We exist during a brief, incredibly special era when stars are shining, galaxies are forming, and complexity is increasing. In the vast sweep of cosmic time, this period of active evolution represents just a tiny fraction of the total story. The universe has this remarkable way of moving from absolute chaos to profound stillness. When we think about the Big Bang, we're talking about the most violent explosion imaginable, yet here we are, billions of years later, drifting toward what scientists call the heat death of the universe. It's like watching fireworks slowly fade into darkness. Black holes represent something fascinating in this cosmic journey. They're not just vacuum cleaners sucking up matter. They actually radiate energy through something called Hawking radiation. Stephen Hawking figured out that these seemingly permanent objects actually evaporate very slowly over unimaginable stretches of time. A black hole with the mass of our sun would take longer to disappear than the current age of the universe, multiplied by trillions upon trillions. The event horizon, that invisible boundary around a black hole, marks a point of no return. Cross that line, and you're committed to falling inward forever. But here's the strange part. From your perspective, falling in would seem normal, almost peaceful. You wouldn't feel the moment you crossed the horizon. Time would flow normally for you, even as the outside universe aged rapidly above you. Quantum mechanics adds another layer of mystery to this cosmic story. At the smallest scales, particles pop in and out of existence constantly. The vacuum of space isn't really empty. It's buzzing with virtual particles, creating and destroying themselves in tiny fractions of seconds. This quantum foam, as physicists call it, might be the foundation everything else is built on. The concept of infinity shows up everywhere in cosmology. Space might be infinite, time might be infinite, and there might be an infinite number of universes parallel to our own. But infinity isn't just a big number, it's a fundamentally different concept. Between any 2 points on a line, there are infinite other points. Between any 2 moments in time, infinite other moments exist. Stars are the universe's recycling centers. They take hydrogen, the simplest element, and forge it into heavier elements through nuclear fusion. When massive stars die in supernova explosions, they scatter these elements across space. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was manufactured inside stellar furnaces. Our galaxy, the Milky Way, contains roughly 400 billion stars. Each star potentially hosts planets, and some of those planets might harbor life. The sheer scale becomes overwhelming when you consider that there are probably 2 trillion galaxies in the observable universe. That's more galaxies than there are trees on Earth. Light has this peculiar property where it always travels at the same speed, regardless of who's observing it. This cosmic speed limit means that when we look at distant objects, we're literally seeing into the past. The light from the nearest star takes over 4 years to reach us. Light from distant galaxies has been traveling for billions of years before entering our telescopes. Dark matter makes up most of the matter in the universe, yet we can't see it directly. It doesn't emit light, doesn't absorb light, but we know it's there because of its gravitational effects. Entire galaxies are held together by dark matter's invisible scaffolding. It's like discovering that most of reality is hidden from our senses. Dark energy is even more mysterious. This force is accelerating the expansion of the universe, pushing galaxies apart at an ever-increasing rate. Eventually, if this continues, galaxies will move so far apart that beings in the distant future won't be able to see beyond their own galaxy. The universe will appear much lonelier. The cosmic microwave background radiation is like the universe's baby picture. This faint glow fills all of space, leftover heat from when the universe first became transparent, about 380,000 years after the Big Bang. Every direction you look, this ancient light surrounds us, carrying information about the universe's earliest moments. Time itself might have had a beginning, which challenges our everyday experience. We're used to thinking that everything has a cause, that every moment follows from the previous moment. But at the very start of the Big Bang, time and space emerged together. Before that moment, the concept of before might not even make sense. The universe appears to be fine-tuned for the existence of complex structures like stars, planets, and life. Change certain fundamental constants by tiny amounts, and atoms wouldn't form, or stars wouldn't shine, or chemistry wouldn't work. This raises profound questions about whether we live in one universe among many, each with different physical laws. Eventually, all the stars will burn out. All the black holes will evaporate. All the protons might decay. The universe will reach a state of maximum entropy, where no more work can be done, no more information can be processed. Yet even in that far future, quantum fluctuations might occasionally create new pockets of order, new possibilities for complexity to emerge from simplicity.